The oldest structures on Earth have witnessed the rise and fall of entire civilizations, yet many of their greatest secrets remain untouched. Built without modern machinery, they continue to astonish with their immense scale, mathematical precision, and remarkable survival across thousands of years. Some stand on isolated mountaintops, others disappear beneath deserts or cliffs, as if deliberately hidden from history itself. Archaeologists have uncovered countless clues, but the most fascinating mysteries refuse to disappear. Every carved stone, hidden chamber, and impossible foundation hints that the ancient world may have possessed knowledge far beyond what we once believed. The deeper we look into these forgotten places, the more extraordinary the past becomes.
In the hills of Campania, southern Italy, the forgotten Roman city of Aclanum preserves walls whose colours have survived nearly 2,000 years. Yet the knowledge that created them has almost completely vanished. Aclanum is located near modern Mirabella Eclano, in the province of Avellino, Italy. Originally founded by the Herpini, a branch of the Samnite people, the settlement became an important Roman municipium after the Social War. It was burned by Lucius Cornelius Sulla in 89 BCE, rebuilt during the Roman imperial period, and gradually declined after a series of earthquakes before being abandoned in the early Middle Ages. Modern archaeological excavations beginning in the 20th century uncovered streets, baths, houses, public buildings, workshops, and remarkably well-preserved painted walls that continue to challenge archaeologists. Among everything discovered at Eclanum, the painted plaster remains one of the site's greatest technological mysteries because modern science can identify many of its ingredients, while still failing to reproduce its extraordinary durability. Fragments recovered from domestic buildings, bath complexes, and public structures retain vivid shades of red, yellow, black, and traces of blue, despite nearly 2 millennia of exposure to groundwater, changing temperatures, biological activity, and repeated earthquakes. Microscopic examination shows that the pigments are not simply resting on the wall surface, but are chemically integrated with successive layers of lime plaster. Researchers have identified familiar Roman materials, including red ochre, rich in iron oxides, yellow ochre, carbon black, and Egyptian blue, the world's earliest known synthetic pigment, first manufactured more than 3,000 years ago. Egyptian blue itself required heating silica, copper compounds, calcium carbonate, and an alkali flux to temperatures approaching 850 to 1,000 degrees Celsius to produce crystals of cuprorivate, an achievement demanding precise control of firing conditions long before modern furnaces existed. Even after identifying these minerals through X-ray diffraction, Raman spectroscopy, scanning electron microscopy, and elemental analysis, conservators still struggle to reproduce coatings that weather in exactly the same way as those preserved at Eclanum. The real puzzle extends beyond pigment composition because the walls demonstrate an exceptional understanding of lime chemistry. Roman painters usually worked using the fresco technique, applying mineral pigments onto fresh lime plaster before carbonation permanently locked color into the wall, as calcium hydroxide reacted with atmospheric carbon dioxide to form calcium carbonate. At Eclanum, however, microscopic studies reveal carefully prepared multi-layer plaster systems with aggregates of different grain sizes, suggesting that craftsmen intentionally controlled porosity, moisture movement, and mechanical strength, rather than merely creating a smooth painting surface. Some fragments contain brick dust mixed into the plaster, introducing reactive silica and alumina that could produce hydraulic compounds capable of increasing durability in humid conditions. Similar reactions have been documented in Roman mortars elsewhere, yet the exact proportions used at Eclanum remain unknown, because identical mineral recipes do not consistently produce identical long-term performance. Two walls containing apparently comparable pigments may display dramatically different resistance to cracking, salt crystallization, or fading, indicating that subtle variations in preparation, curing conditions, or organic additives may have played a significant role. No surviving Roman technical text explains those details, leaving modern laboratories with impressive analytical data, but no complete manufacturing formula. This mystery becomes even more intriguing because many pigments respond differently to environmental stress. Egyptian blue is chemically stable and resistant to ultraviolet radiation, while iron oxide pigments can survive for thousands of years with minimal color change. Carbon black remains remarkably durable when protected within mineral plaster, yet all of these materials depend on the surrounding matrix for long-term preservation. If the plaster develops microscopic fractures, water-carrying dissolved salts can enter, crystallize during evaporation, and gradually destroy the painted surface from within. The walls of Eclanum have certainly experienced repeated seismic events, including destructive earthquakes recorded in southern Italy during late antiquity, yet many painted fragments remained attached to their original support. That resilience suggests an unusually effective bond between successive plaster layers, but researchers still debate whether this resulted primarily from material composition, curing methods, or construction techniques that have disappeared from history. The painted walls also reveal remarkable organizational skills because producing frescoes of consistent quality required coordinated teams rather than isolated artists. Lime plaster had to be prepared weeks or even months before use. Pigments had to be processed into uniform particle sizes. Surfaces had to be divided into daily working sections known as journate, and painters needed to complete each section before carbonation hardened the plaster permanently. Any delay would leave visible joints or weaken pigment adhesion. Yet despite this demanding schedule, many surviving fragments display smooth transitions across adjoining sections, implying careful planning that cannot be reconstructed from archaeological remains alone. The finished paintings survived, but the workflow that created them disappeared. As researchers attempt to understand the walls, the rest of Eclanum reveals equally impressive engineering, although with fewer unanswered questions than its remarkable pigments. Excavations uncovered a sophisticated drainage network beneath the streets, where underground sewers maintained gradients generally estimated at less than 1%, allowing wastewater to flow efficiently without eroding the masonry channels. Achieving such precision across an expanding urban landscape required accurate surveying methods using instruments such as the chorobates and groma. Yet the practical techniques that enabled surveyors to maintain consistent elevations over long distances remain only partially understood, because no construction records survive. The city's bath complexes provide another example of Roman technical expertise through extensive hypercaust heating systems. Brick pillars supported suspended floors, while furnaces circulated hot air beneath rooms and inside hollow wall tiles, creating controlled indoor temperatures. Archaeological evidence demonstrates excellent heat distribution, but calculations involving airflow, fuel consumption, and thermal efficiency had to be solved empirically, because no engineering manuals explain how builders optimized these installations for structures of different sizes. The completed system survives, while the design process remains largely invisible. Water management throughout Eclanum was equally advanced. Lead distribution pipes, reservoirs, and storage tanks supplied public buildings and private houses, reflecting hydraulic principles widely applied across the Roman world. Maintaining relatively stable water pressure across neighborhoods of varying elevation required careful planning of gradients, storage capacity, and flow regulation. Although Roman authors such as Frontinus described aspects of aqueduct administration, They left few practical details explaining how individual towns balanced local distribution networks with such consistency. The city's streets and foundations likewise demonstrate engineering choices refined through centuries of experience. Roads were constructed with multiple structural layers of compacted stone, and paving blocks capable of resisting settlement even on uneven terrain, while walls incorporated techniques including opus reticulatum, opus latericium, and opus mixtum that distributed structural loads efficiently and allowed damaged sections to be repaired without rebuilding entire buildings. Aeclanum also endured repeated seismic activity associated with the tectonic environment of the southern Apennines, yet numerous structures remained standing long enough to be repaired and reused, suggesting that Roman builders had developed practical strategies for improving resilience, even if they lacked a scientific theory of earthquakes. Located along the Danube in northern Bulgaria, Oescus preserves one of the Roman world's most overlooked engineering mysteries, where mosaics, concrete, hydraulic systems, and the remains of an enormous bridge continue to challenge modern archaeological science. Oescus is an ancient Roman city located near today's village of Gigan in northern Bulgaria, approximately 5 kilometers south of the Danube River. Originally established beside a Thracian settlement, it became the permanent base of Legio V Macedonica during the 1st century AD, before Emperor Trajan elevated it to the status of a Roman colonia around AD 106. Although the site had attracted antiquarian attention for centuries, systematic archaeological excavations only began during the early 20th century and expanded significantly after the 1940s, revealing forums, baths, temples, workshops, streets, residential quarters, water infrastructure, and some of the finest Roman mosaics discovered anywhere in the Balkans. Excavated remains now cover more than 100,000 square meters, yet this represents only part of a city that once occupied several dozen hectares. Among everything uncovered at Oescus, the House of Fortuna has generated perhaps the greatest technological puzzle because its extraordinary mosaic floors remain remarkably well preserved after nearly 17 centuries, despite exposure to earthquakes, seasonal flooding, changing groundwater conditions, and long periods of abandonment. The largest surviving composition depicts the goddess Fortuna, surrounded by geometric borders, birds, floral ornaments, and carefully arranged colored tesserae cut from limestone, marble, ceramic, and colored glass. Archaeologists estimate that individual mosaics contain hundreds of thousands of tiny pieces, many measuring only 1 to 2 centimeters across, each positioned with astonishing precision to create smooth transitions of color and perspective. Scientific analyses using petrographic microscopy, X-ray diffraction, and scanning electron microscopy have shown that the durability of these floors depends not only on the visible stones, but also on the sophisticated multi-layer foundation beneath them. Roman builders first created a compact stone base known as the statumen, followed by a thick rudous layer of crushed stone mixed with lime mortar, then a finer nucleus composed of lime, sand, and carefully graded aggregates, before finally placing the tesserae into a thin bedding layer. This layered structure distributed mechanical stress while allowing slight movement without causing widespread cracking, explaining why large sections remain almost perfectly level after more than 1,600 years. Yet the greatest mystery lies inside the mortar itself. Modern laboratory studies consistently identify calcium carbonate crystals, hydrated lime products, and microscopic mineral bonds that continue to strengthen over time through slow chemical reactions with groundwater and atmospheric carbon dioxide. Similar self-healing behavior has recently been documented in several Roman mortars across the Mediterranean, where dissolved calcium can recrystallize inside microscopic fractures, naturally sealing tiny cracks before they expand into structural failures. At Oescus, however, researchers still cannot reconstruct the precise mixture that produced these exceptionally durable foundations, because no written construction manuals survive for this specific workshop. The proportions of lime, water, aggregate, firing temperature, curing period, and local mineral additives remain uncertain, while even slight changes in these variables could significantly alter the long-term performance of the material. Equally remarkable is the stability of the pigments. Red tones produced from iron-rich minerals, black from carbon-based materials, white from marble, green from copper-bearing minerals, and colored glass tesserae have retained much of their original appearance despite nearly 2 millennia of oxidation, moisture, biological growth, and temperature fluctuations. Scientists understand the mineral sources of these colors, yet the complete production process that allowed them to resist fading so effectively is still only partially understood. The engineering sophistication visible beneath these decorative flaws naturally raises broader questions about the city itself. Oescus stood on the floodplain of one of Europe's largest rivers, where unstable alluvial sediments, seasonal flooding, and fluctuating groundwater would normally threaten heavy masonry construction. Excavations nevertheless reveal buildings whose foundations remain remarkably stable after centuries of environmental change. Beneath many structures, archaeologists identified carefully prepared sequences of gravel, compacted stone, sand, and lime mortar, arranged to improve drainage and spread structural loads. Modern geotechnical engineering follows similar principles, but Roman builders possessed neither mechanical drilling equipment nor mathematical soil models. The archaeological record demonstrates that they understood local ground behavior well enough to support temples, administrative buildings, bath complexes, and large residential houses, although exactly how they evaluated soil stability before construction remains unknown. That understanding extended into water management, another field in which Oescus demonstrates remarkable technical competence. Excavations have uncovered aqueducts, underground drains, reservoirs, distribution channels, and lead pipelines supplying baths, fountains, and private residences. Because the surrounding terrain lacks the dramatic elevation changes seen in many other Roman cities, engineers had to maintain extremely precise hydraulic gradients to keep water flowing efficiently while avoiding excessive pressure that could damage pipes. Sections of surviving conduits reveal carefully controlled slopes over considerable distances, suggesting detailed surveying before construction began. Roman instruments such as the groma, corobats, and dioptra are known from historical sources, yet archaeologists still debate how surveyors consistently achieved such accuracy across an expanding urban landscape, using only these relatively simple devices. The city's structural materials present another unanswered question. Walls throughout Oescus were constructed using combinations of fired brick, limestone blocks, and opus caementicium, the famous Roman concrete whose long-term durability continues to attract scientific attention. Laboratory investigations of Roman concrete from numerous Mediterranean sites have identified rare calcium-aluminum silicate hydrate phases, together with lime clasts capable of promoting limited self-repair when cracks develop. Although Oescus does not preserve concrete on the monumental scale seen at Roman harbors, surviving masonry demonstrates comparable resistance to weathering. Researchers still cannot determine whether local builders imported volcanic materials from distant regions, relied entirely on local aggregates, or modified traditional Roman recipes to suit the geology of the lower Danube. The greatest engineering achievement associated with Oescus once extended far beyond the city walls. In AD 328, Emperor Constantine inaugurated an enormous bridge linking Oescus with Suceava on the opposite bank of the Danube. Ancient sources attribute the design to the engineer Theophilus Patricius and describe a structure approximately 2.5 kilometers long, with roughly 1.3 kilometers crossing the river itself, making it one of the longest bridges ever built in the Roman world. Constructing such a crossing required foundations capable of resisting powerful currents, drifting ice, seasonal floods, and unstable river sediments. Only fragments of foundations and scattered archaeological evidence survive today, leaving historians unable to reconstruct the complete construction sequence. Massive cofferdams, timber piles, lifting systems, cranes, and coordinated labor must all have played essential roles, yet almost every temporary engineering solution disappeared once the bridge was completed, leaving the finished monument but not the methods that created it. In northeastern Bulgaria, beneath the modern city of Silistra near the Danube, lies ancient Durostorum, a Roman frontier fortress whose greatest mystery is not its walls, but a painted tomb that has survived almost perfectly for more than 16 centuries. Silistra is the site of the Roman city of Durostorum. Established as a military fortress on the lower Danube during the late 1st century AD and becoming the permanent base of Legio XI, Claudia. Archaeological excavations carried out throughout the 20th century revealed extensive Roman defences, streets, water infrastructure, and, in 1942, an extraordinary underground mausoleum dating to the middle of the 4th century AD. Today, Silistra Roman Tomb is recognized as one of the finest preserved examples of late Roman funerary painting in southeastern Europe and has been included on Bulgaria's UNESCO tentative list because of its exceptional artistic and historical significance. Among everything uncovered at Durostorum, the tomb remains the greatest technological puzzle because nearly every surface inside the burial chamber is covered with remarkably preserved frescoes despite spending more than 1,600 years underground. Archaeologists have identified portraits of servants, floral garlands, peacocks, hunting scenes, geometric ornaments and architectural motifs painted across the vaulted chamber with an artistic quality rarely preserved elsewhere in the Roman world. Scientific analyses show that many of the pigments were derived from naturally occurring minerals, including iron oxides for red and yellow tones, carbon black for dark outlines, and calcium-based white pigments applied over carefully prepared lime plaster. These materials were common throughout the Roman Empire, yet the exceptional state of preservation at Silistra cannot be explained simply by the choice of pigments. The paintings retain unusually vivid color transitions, delicate brushwork, and sharply defined outlines that normally deteriorate after centuries of exposure to moisture, salt migration, and biological activity. Researchers therefore believe that the survival of the murals resulted from a combination of sophisticated plaster preparation, stable underground microclimatic conditions, and the tomb's fortunate sealing shortly after antiquity. But the precise contribution of each factor remains impossible to quantify because the original construction process was never recorded. The engineering of the plaster itself presents another unresolved question. Roman wall paintings were normally executed using multiple layers of lime plaster applied with carefully graded aggregates before pigments were painted onto the fresh surface using the fresco technique. Microscopic examination of the Silistra murals has confirmed this layered structure, yet the exact composition differs subtly from many contemporary sites. Some samples reveal exceptionally dense crystalline bonding between the lime binder and mineral aggregates, producing a surface that resisted flaking for more than 16 centuries despite seasonal temperature fluctuations above ground. Modern conservation scientists understand the underlying chemistry of lime carbonation, in which calcium hydroxide reacts with atmospheric carbon dioxide to form stable calcium carbonate, but they cannot fully reconstruct the original mixing ratios, curing conditions, or craftsmanship that produced such long-term durability. Small variations in aggregate size, moisture content, or curing time can dramatically influence the final mechanical strength, and those practical details disappeared with the craftsmen themselves. The tomb also raises questions about Roman environmental engineering. Unlike monumental temples exposed to wind and rain, this chamber remained buried beneath layers of soil that created an unusually stable internal environment. Measurements collected during modern conservation projects show that underground temperature and humidity fluctuate far less than conditions outside, greatly slowing chemical weathering and biological growth. Even so, countless Roman tombs with similar underground settings have lost most of their paintings through salt crystallization, groundwater infiltration, or microbial damage. Silistra somehow escaped much of this deterioration. Archaeologists suspect that the builders selected a location with favorable geological drainage while designing masonry capable of limiting water penetration. Yet no surviving Roman text explains how local engineers evaluated underground moisture or predicted the long-term behavior of the surrounding sediments. The result is a monument whose preservation appears almost accidental, although accumulating evidence suggests that careful engineering decisions played an important role. As remarkable as the tomb itself is, it existed within one of Rome's most strategically important frontier cities. Durostorum occupied a commanding position along the lower Danube, one of the empire's principal defensive frontiers stretching for hundreds of kilometers. The fortress protected military crossings while controlling trade and communication between the Balkans and territories north of the river. Maintaining a permanent legion required enormous logistical organization. A Roman legion typically numbered around 5,000 to 6,000 soldiers, accompanied by civilians, craftsmen, merchants, and support personnel who transformed the fortress into a thriving urban center. Supplying this population demanded reliable water, drainage, storage facilities, and transportation infrastructure capable of operating throughout the year. That necessity makes another engineering question particularly interesting. The Danube is Europe's second longest river, extending approximately 2,850 kilometers. From Germany to the Black Sea, yet relying directly on river water presented obvious challenges. Seasonal flooding, suspended sediment, and contamination made untreated river water unsuitable for continuous urban consumption. Excavations at Durostorum have revealed wells, cisterns, drainage channels, and water management structures, demonstrating that Roman engineers invested heavily in hydraulic infrastructure. What remains uncertain is the complete configuration of the city's water supply network, because much of ancient Durostorum lies beneath the modern city of Silistra. Geophysical surveys suggest additional buried structures, but large-scale excavation is impossible in densely occupied urban districts, leaving substantial portions of the hydraulic system hidden from investigation. The fortress walls provide another example of Roman engineering that is understood in principle but not in every practical detail. Built on terraces overlooking the Danube, the defenses endured repeated military crises involving Goths, Huns, Avars, Slavs, and later Byzantine reconstruction. Archaeological evidence shows multiple rebuilding phases rather than a single uninterrupted structure. Yet portions of the Roman masonry continued serving successive civilizations for centuries. The durability largely resulted from carefully cut limestone blocks combined with lime mortar containing crushed ceramic fragments, a material capable of producing hydraulic reactions that improved resistance to moisture. Laboratory analysis confirms the presence of these ceramic additives, similar to other Roman mortars across the empire, but local variations in raw materials and construction techniques make it difficult to reproduce exactly the mechanical performance observed in surviving structures. Even modern conservation projects continue studying why certain Roman mortars maintain structural integrity after nearly 2,000 years, while many later constructions deteriorate much more rapidly. The layout of Durostorum reflects the remarkable precision of Roman military planning. Excavated streets follow the familiar, orthogonal grid characteristic of legionary fortresses, organizing barracks, workshops, administrative buildings, and storage facilities with impressive regularity. Roman surveyors achieved this alignment using instruments such as the groma for establishing right angles and the chorobates for measuring level gradients during hydraulic construction. Ancient authors, including Vitruvius, described these instruments, yet written descriptions alone cannot reveal the practical expertise required to transfer geometric plans onto uneven terrain with consistent accuracy across an entire fortress. Archaeological remains preserve the finished result, but almost none of the temporary surveying markers, wooden measuring devices, or construction procedures that transformed theoretical geometry into functioning infrastructure. The granite hills near Guimarães in northern Portugal are home to Castro de Sabroso, which preserves the silent remains of an Iron Age fortress whose massive stone walls have resisted gravity, weather, and time for more than 2,000 years. Castro de Sabroso is an Iron Age hill fort first identified through 19th century archaeological surveys and later investigated by systematic excavations that revealed multiple defensive walls, circular stone houses, streets, workshops, and evidence of continuous occupation between approximately the 4th century BCE and the early Roman period. At first glance, Castro de Sabroso appears to resemble dozens of other settlements belonging to the Castro culture that flourished across northwestern Iberia before Roman conquest. Yet the closer archaeologists examine its architecture, the more remarkable one question becomes. How did Iron Age builders, working without cement, steel, cranes, or written engineering manuals, construct defensive walls capable of surviving over 20 centuries while standing on uneven granite bedrock exposed to heavy Atlantic rainfall? Unlike Roman forts, whose construction methods are extensively documented, the engineering knowledge behind these earlier hill forts survives only in stone, forcing researchers to reconstruct an entire technological tradition from the structures themselves. The defensive walls immediately draw attention because they were built entirely using dry stone masonry. Instead of relying on mortar to bind the blocks together, builders carefully selected granite stones of different shapes and sizes before locking them together through weight, friction, and geometry alone. Excavations show that several stretches of wall measure approximately 2 to 3 meters in thickness, creating formidable barriers around the settlement despite the absence of any chemical binding material. Modern structural engineers recognize that dry stone construction behaves differently from mortared masonry because it can redistribute stress through thousands of contact points between individual stones, allowing slight movement during ground settlement without catastrophic collapse. Even so, the precision required remains astonishing. Every irregular block had to contribute to the stability of those surrounding it, meaning a single misplaced stone could weaken an entire section. After more than 2,000 years of seasonal temperature changes, erosion, biological growth, and countless Atlantic storms, significant portions of these walls continue to stand, suggesting that their builders possessed an exceptional practical understanding of load distribution, despite leaving behind no written explanation of their methods. This achievement becomes even more impressive when the material itself is considered. Granite is one of the hardest commonly used construction stones, typically possessing a compressive strength exceeding 100 megapascals and often reaching more than 200 megapascals, depending on mineral composition. Such durability explains why the walls have endured, but it also raises another puzzle. Working granite without iron saws, explosives, or modern cutting equipment required extraordinary skill. Archaeological evidence from Iron Age Iberia indicates that craftsmen used iron picks, wedges, hammers, and controlled fracturing techniques to detach usable blocks from natural outcrops. Yet exactly how construction teams consistently produced thousands of suitable stones with limited technology remains incompletely understood, because quarrying areas associated with Castro de Sabroso have not been preserved well enough to reconstruct every stage of production. As researchers continue examining the settlement, another pattern gradually emerges. The walls do not simply surround the hill in geometric shapes. Instead, they closely follow the contours of the landscape, bending around granite outcrops and incorporating natural cliffs into the defensive system. This approach dramatically reduced the quantity of stone required, while simultaneously strengthening vulnerable sections. Modern military engineers describe this philosophy as terrain integration, where natural landforms become active components of defensive architecture. Without aerial surveys, digital mapping, or precision instruments, Iron Age builders nevertheless achieved a layout that maximized visibility across surrounding valleys while minimizing exposed approaches. Whether this resulted from generations of accumulated experience or sophisticated surveying techniques passed orally remains impossible to determine, because no measuring devices or construction manuals have ever been recovered. The organization inside the walls presents another intriguing aspect of the settlement. Excavations uncovered clusters of circular dwellings connected by narrow stone-paved pathways and shared open spaces instead of randomly scattered buildings. Individual houses commonly measure between 4 and 6 meters in diameter, while thicker exterior walls provided insulation against the humid Atlantic climate. The repetition of similar dimensions throughout different construction phases has led some archaeologists to suggest that builders followed standardized planning principles, even though no written system of measurement survives from the local communities. Such consistency does not necessarily imply formal mathematics comparable to later Roman engineering, but it strongly indicates the existence of well-established construction traditions transmitted across generations through apprenticeship rather than texts. The settlement also demonstrates an unexpectedly sophisticated relationship with water. Northern Portugal receives abundant annual rainfall, often exceeding 1,000 millimeters, depending on elevation and local climate. Despite these conditions, excavations reveal surprisingly little evidence of prolonged water damage within the principal residential areas. Instead of monumental underground sewers like those developed centuries later by the Romans, Castro de Sabroso appears to have relied upon carefully graded surfaces, subtle slopes, stone paving, and the natural permeability of fractured granite to direct runoff away from homes. The complete drainage network can no longer be reconstructed because erosion and later occupation disturbed parts of the site. Yet the overall preservation suggests that effective water management formed an essential part of the original design. Daily life within the hill fort also reflects technological abilities extending beyond defensive architecture. Excavations recovered rotary querns for grinding grain, spindle whorls associated with textile production, ceramic vessels manufactured locally, iron tools, and metallurgical waste indicating that metalworking occurred within or near the settlement. Iron production during this period required furnaces capable of reaching temperatures approaching 1200 degrees Celsius to reduce iron ore into workable blooms before repeated forging removed impurities. Although similar techniques are documented elsewhere across Iron Age Europe, the precise organization of production at Castro de Sabroso remains uncertain because only fragments of industrial activity have survived. Nevertheless, these discoveries confirm that the community possessed skilled craftspeople capable of supporting substantial construction projects over many generations. Modern archaeological methods continue revealing new information without fully resolving the settlement's greatest engineering puzzle. Detailed topographic surveys, digital photogrammetry, three-dimensional modeling, microscopic stone analysis, and geographic information systems now allow researchers to examine construction techniques with a precision unimaginable only decades ago. These technologies can measure wall deformation, identify quarry sources, and reconstruct collapsed sections virtually, yet they cannot recover the practical knowledge carried in the minds of Iron Age master builders. The stones preserve the final result, but remain silent about the countless decisions made during construction. Perched along the Atlantic coast in Viana do Castelo, northern Portugal, Citania de Santa Luzia stands on a rugged granite hill where an Iron Age community accomplished a feat that still raises engineering questions today. Long before Roman surveyors introduced standardized planning across Iberia, hundreds of people transformed an uneven mountaintop into a fortified settlement whose organization continues to challenge archaeologists. Citania de Santa Luzia is an Iron Age hill fort of the Castro culture, first identified through archaeological investigations in the late 19th century and systematically excavated during the 20th century after stone walls and circular structures emerged beneath vegetation. Excavations, supported by ceramic typology, Roman artifacts, stratigraphy, and radiocarbon dating from comparable Castro settlements, indicate that the site was mainly occupied from around the 1st century BC into the early centuries of Roman rule. Sitting more than 100 meters above sea level, with commanding views over the Lima estuary and the Atlantic coastline, the settlement controlled one of the most strategic landscapes in northwestern Iberia. What immediately separates Santa Luzia from many ancient settlements is not the size of its walls, but the landscape itself. Instead of choosing a broad plateau or fertile valley, its builders selected an irregular granite summit, broken by steep slopes, exposed bedrock, and constantly changing elevations. Modern digital terrain models reveal that the available construction surface was fragmented into countless natural levels, yet the finished settlement appears remarkably organized rather than chaotic. This leads directly to the greatest unresolved question surrounding the site. How did Iron Age engineers plan an entire community on terrain that was never naturally suitable for urban construction? The problem is far greater than simply placing houses wherever flat ground existed. Archaeological mapping shows that the settlement contains circular dwellings, enclosed family compounds, paved pathways, defensive walls, stairways, and communal spaces that connect logically across the hill without wasting valuable space. Every structure had to fit within an environment where differences in elevation could change dramatically over only a few meters. Today, archaeologists reconstruct this layout using drone photogrammetry, LiDAR, geographic information systems, and three-dimensional terrain modeling. Yet the original builders accomplished the same feat without maps, modern surveying instruments, or surviving written plans. No measuring rods, construction drawings, or engineering manuals have ever been recovered from the site. Even more remarkable, the settlement avoids the appearance of random expansion. Pathways consistently link important areas, circulation remains efficient, despite the irregular topography, and the organization suggests that someone understood the entire landscape before construction reached its final form. Whether this knowledge depended on sophisticated visual surveying, generations of accumulated experience, or planning techniques, now completely lost, remains unknown. That mystery becomes even more striking when examining the settlement's drainage. Granite hills receive heavy Atlantic rainfall, and northern Portugal averages well over 1,000 millimeters of precipitation annually. Water flowing uncontrolled across exposed rock would rapidly erode foundations and destabilize buildings. Yet, excavations indicate that many houses were deliberately positioned on slightly inclined platforms, where rainwater naturally escaped toward narrow channels between stones before continuing down the hillside. Rather than constructing massive drainage tunnels, the builders appear to have transformed the mountain itself into a functioning hydraulic system. Several pathways also follow gradients that naturally reduce water accumulation, suggesting that hydrology influenced urban planning from the beginning. Modern researchers can explain how the system works, but cannot explain how its designers calculated slopes with such consistency using only Iron Age technology. The defensive walls introduce another unresolved engineering question. Santa Luzia belongs to the Castro tradition of dry stone construction, where massive granite blocks were assembled without mortar. Thousands of freeze-thaw cycles, Atlantic storms, earthquakes, vegetation growth, and more than 2,000 years of weathering should have caused widespread collapse. Yet substantial sections remain standing. Structural engineers studying similar Iberian hill forts note that stability depends on carefully balancing block size, contact surfaces, weight distribution, and foundation placement, rather than adhesive materials. Every stone had to contribute to the overall equilibrium of the wall. What remains uncertain is how builders selected individual blocks with sufficient precision while working almost entirely with hard granite, using Iron Age iron tools. Laboratory studies demonstrate that granite ranks between 6 and 7 on the Mohs hardness scale, making quarrying and shaping labor-intensive, even with modern equipment. Archaeologists still debate whether blocks were finished directly at nearby outcrops or transported after partial shaping, because evidence for large extraction zones around Santa Luzia remains surprisingly limited. Its fortifications also reveal a sophisticated understanding of defense without following the geometric regularity seen in later Roman military architecture. Instead of straight walls surrounding rectangular streets, Santa Luzia uses multiple defensive circuits that bend around the contours of the hill. Entrances rarely provide direct access into the settlement, forcing movement through narrow, curved passages where attackers would lose momentum and expose their flanks. Computer simulations of comparable Castro hill forts suggest that these indirect gateways significantly increase defensive effectiveness by slowing advancing groups while giving defenders superior visibility. Yet no evidence suggests that the builders possessed formal military geometry or mathematical theories of fortification. Their solutions appear to emerge from practical observation refined across generations, rather than documented engineering principles. Equally intriguing is the selection of foundation locations. Building directly on exposed granite minimizes settlement, reduces differential movement, and greatly improves long-term stability. Modern geotechnical engineers routinely seek competent bedrock before constructing heavy structures, but Santa Luzia's builders consistently exploited naturally stable outcrops across an uneven mountain without modern geological surveys. Excavation profiles repeatedly show walls anchored where granite reaches the surface, while weaker deposits were often avoided. Whether these choices resulted from careful empirical testing or inherited geological knowledge remains impossible to determine because no written tradition survives. The organization of movement throughout the settlement presents another puzzle. Circular houses are notoriously difficult to arrange efficiently. because they naturally create irregular gaps between structures. Nevertheless, Santa Lucia's residential compounds maximize usable space while preserving circulation routes that connect homes, defensive sectors, and communal areas. Archaeologists observing settlement evolution often expect organic villages to develop dead ends, awkward expansions, and disconnected neighborhoods. Instead, Santa Lucia displays an unexpectedly coherent circulation network. Some researchers argue that the community expanded according to an unwritten planning tradition rather than spontaneous growth, although no consensus explains how such continuity could be maintained across multiple generations. Material logistics add yet another unanswered question. Granite blocks weighing several hundred kilograms had to reach elevated construction areas across steep slopes before cranes, wheeled transport adapted to mountains, or advanced lifting machines existed locally. Experimental archaeology demonstrates that wooden sledges, rollers, rope systems, and coordinated human labor can move heavy stones, but no direct archaeological evidence identifies which method Santa Lucia employed. Without preserved timber equipment or construction records, every reconstruction remains hypothetical. Velea was a Roman mountain town in northern Italy that preserved one of the empire's most intriguing technological puzzles. Among its ruins, archaeologists uncovered the largest surviving bronze administrative tablet ever produced by Rome, a masterpiece whose manufacturing process remains only partially understood. Velea is an ancient Roman municipality located approximately 40 kilometers south of modern Piacenza, on the northern slopes of the Apennine Mountains. The city was accidentally rediscovered in the early 18th century after local farmers repeatedly uncovered carved stones while cultivating their fields. Systematic excavations began in 1747 under the Duchy of Parma after the discovery of an enormous inscribed bronze tablet buried beneath collapsed structures, revealing a remarkably preserved forum, basilica, temples, houses, and public infrastructure that had remained hidden for nearly 15 centuries. The discovery immediately attracted scholars because the bronze monument, now known as the Tabula Alimentaria Veliana, was unlike anything previously found in the Roman world. Measuring nearly 3 meters in width, approximately 1.4 meters in height, and weighing around 200 kilograms, it remains the largest surviving bronze inscription from ancient Rome. More than 1,000 carefully engraved lines record landowners, estates, and financial arrangements supporting Emperor Trajan's Alimenta program, a public welfare system that provided assistance for children across Italy. While historians can read almost every word on the tablet, the engineering required to manufacture such an object remains surprisingly elusive. Producing a bronze sheet of this scale would have demanded extraordinary control over metallurgy. Ancient bronze generally consists of copper, alloyed with roughly 8 to 12% tin, although minor quantities of lead, iron, and arsenic often appear depending on the ore source. Experimental archaeology demonstrates that casting large bronze objects becomes increasingly difficult as dimensions increase because molten metal cools unevenly, creating internal stresses capable of warping or cracking the finished product. Modern foundries overcome these problems through carefully controlled furnace temperatures, standardized molds, and monitored cooling cycles, yet Roman craftsmen possessed none of these instruments. Even so, the Velea tablet survived with remarkable structural stability after nearly 2,000 years underground. The manufacturing sequence itself remains uncertain. Some metallurgists suggest the tablet was cast as a single massive plate before extensive hammering and surface finishing removed irregularities. Others propose that repeated cycles of heating and mechanical working gradually flattened the metal into its final dimensions. Both methods are technically possible, yet neither has been demonstrated conclusively because no Roman workshop describing the production of monumental bronze documents has ever been discovered. The archaeological evidence preserves the completed object, but almost none of the tools, molds, or temporary equipment that created it, leaving researchers to reconstruct an industrial process from the finished result alone. Equally remarkable is the precision of the inscription. Thousands of Latin letters remain aligned across horizontal rows, with consistent spacing despite covering an exceptionally large surface. Microscopic examination reveals deliberate engraving by skilled artisans using hardened iron tools, yet almost no visible guidelines survive to explain how the craftsman maintained such regularity over several square meters of polished bronze. A deviation of only a few millimeters early in the layout would have become dramatically amplified by the final lines, but the inscription maintains an impressive visual consistency throughout. Whether Roman engravers relied upon inked strings, calibrated rulers, hidden reference marks, or sophisticated measuring frames remains unknown, because the production methods disappeared long before written technical manuals could preserve them. Scientific analyses have provided valuable clues without solving every question. X-ray fluorescence and metallographic examinations identify the alloy composition and reveal evidence of mechanical finishing, while corrosion studies explain why much of the inscription remained legible after centuries beneath the soil. These investigations confirm the remarkable quality of Roman metallurgy, but cannot reconstruct the organization of the workshops, the number of craftsmen involved, or the exact sequence of manufacturing operations. The technology is visible in the artifact itself, while the practical knowledge that produced it has largely vanished. The engineering mysteries continue beyond the bronze tablet. Velia occupied an elevation of roughly 450 meters above sea level on the geologically unstable northern Apennines, where clay-rich sediments and weathered rock are naturally susceptible to landslides. Modern construction on comparable slopes often requires reinforced retaining structures, drainage systems, and continuous geotechnical monitoring. Roman engineers, however, established an urban center complete with monumental public buildings, paved streets, and administrative complexes that remained functional for centuries. Excavations indicate that the forum was constructed upon carefully prepared artificial terraces supported by retaining walls and multiple foundation layers. Archaeologists have identified sequences of compacted stone, gravel, and drainage material beneath parts of the public square, suggesting that builders intentionally reduced water accumulation inside the slope. Although Roman engineers possessed no mathematical theory equivalent to modern soil mechanics, they clearly understood through observation that controlling groundwater significantly improved long-term stability. The precise calculations guiding these foundations remain undocumented because no construction records from Velea have survived. Water management throughout the settlement demonstrates similar sophistication. Stone drains, underground channels, and collecting basins were integrated beneath streets and public spaces to direct runoff away from critical foundations. Hydrological studies show that increasing pore water pressure is one of the principal triggers of slope failure, making drainage essential for any settlement built on unstable terrain. Whether Roman builders understood the underlying physics or simply relied upon generations of empirical experience remains impossible to determine, yet their solutions achieved results that protected the city for hundreds of years. Supplying fresh water to a mountain settlement introduced another engineering challenge. Springs located at higher elevations fed reservoirs and distribution networks through gravity, requiring gradients carefully controlled over considerable distances. Even minor surveying errors could have interrupted water flow or accelerated erosion inside channels. Roman surveyors employed instruments such as the chorobates and groma, but historians continue debating the degree of accuracy these devices could achieve across steep, irregular landscapes. The surviving hydraulic infrastructure demonstrates that practical precision frequently exceeded expectations based solely upon the surviving instruments. The city's eventual disappearance remains another unresolved chapter. Geological investigations indicate that repeated landslides affected the surrounding slopes over many centuries, while archaeological evidence also points toward gradual economic decline during the late Roman Empire. Rather than a single catastrophic event, many researchers now favor a combination of progressive instability, changing trade networks, and demographic contraction that slowly transformed a thriving municipality into a buried archaeological landscape. Even this interpretation, however, cannot fully explain the complex sequence of deposits covering different parts of the city. Augusta Raurica, located near Basel, Switzerland, preserves one of the Roman world's greatest engineering puzzles, where remarkable technology survived for nearly 2,000 years, while the knowledge that created it almost completely disappeared. Augusta Raurica is a Roman colony founded around 44 BCE by Lucius Munatius Plancus on the south bank of the Rhine River. Although parts of the city had been known for centuries, systematic archaeological excavations began during the 19th century and accelerated throughout the 20th century, eventually revealing nearly 200 hectares of streets, workshops, temples, baths, theatres, and residential districts. Researchers estimate that during the 2nd century CE, the settlement supported approximately 15,000 to 20,000 inhabitants, making it one of the largest Roman cities north of the Alps. Yet among its monumental buildings, the greatest mystery may not be its architecture, but the industrial technology that once powered its economy. The strongest evidence comes from the extensive metalworking district uncovered during excavation. Archaeologists have identified furnaces, casting debris, crucibles, molds, slag deposits, unfinished bronze objects, and ironworking waste distributed across specialized workshops, demonstrating that Augusta Raurica was not merely importing finished products, but manufacturing them on a considerable scale. Scientific examination using optical microscopy, scanning electron microscopy, X-ray fluorescence spectroscopy, and metallographic analysis reveals copper alloys containing carefully controlled proportions of tin and lead, while iron artifacts display microstructures indicating repeated cycles of forging, reheating, and controlled cooling. These analyses clearly demonstrate highly skilled craftsmanship, yet they expose an unexpected contradiction. Modern science can determine the chemical composition of finished objects with remarkable precision, but it still cannot reconstruct the complete manufacturing sequence that produced them. The furnaces themselves survive only as damaged foundations. The bellows vanished long ago because they were built from organic materials, and no written manual explains how Roman craftsmen consistently maintained temperatures exceeding 1,000 degrees Celsius while producing alloys with surprisingly uniform mechanical properties. Experimental archaeologists have successfully recreated individual stages of Roman metallurgy, but every reconstruction depends on assumptions because the archaeological record preserves only fragments of the original production system. The city therefore records the products of sophisticated engineering while concealing the practical knowledge that allowed ordinary craftsmen to repeat the same results generation after generation. That missing knowledge becomes even more intriguing when the origin of the raw materials is considered. Lead isotope analysis suggests that some metals circulating through Augusta Raurica originated from mining regions separated by hundreds of kilometers, including areas within Gaul, Germania, and the Iberian Peninsula. Such evidence demonstrates that the colony participated in an extensive commercial network stretching across the Roman Empire. However, imported ore alone cannot explain the remarkably consistent quality of locally manufactured objects. Ancient metallurgists somehow adjusted different raw materials to produce reliable alloys despite natural variations in mineral composition. Without standardized laboratory instruments, digital thermometers, or chemical testing equipment, they repeatedly achieved results that modern laboratories can identify but still struggle to explain operationally. The technical expertise clearly existed, yet the methods themselves disappeared with the workshops that once dominated the industrial quarter. The city's construction techniques present another layer of uncertainty. Augusta Raurica occupies terrain consisting of sandstone, river sediments, and sloping ground overlooking the Rhine, conditions that normally create long-term challenges for heavy masonry. Nevertheless, monumental buildings including the theatre, forum, baths, and large residential complexes remain structurally stable for centuries. Geological investigations indicate that Roman builders prepared multi-layered foundations composed of compacted stone, gravel, and mortar, rather than relying on deep, modern-style piles. Archaeological excavation reveals the finished foundation systems but not the planning process that determined layer thickness, material selection, or load distribution. Engineers can calculate why these foundations function today, yet they still cannot identify the empirical methods Roman surveyors used to optimize them before construction even began. The mortar itself preserves another unanswered question. Mineralogical analyses using X-ray diffraction and electron microscopy have identified lime, locally available aggregates, crushed ceramic fragments, and hydraulic reaction products comparable to those found in other durable Roman concretes. Even so, samples collected from different structures often display noticeably different microstructures and mechanical performance despite being constructed within similar periods. Researchers increasingly suspect that builders deliberately modified mortar recipes according to the intended function of each building, rather than following a single standardized formula. Unfortunately, the proportions, preparation sequence, and quality control procedures were never recorded, leaving only hardened material whose exceptional durability survives long after the construction techniques vanished. These engineering decisions extended beneath the streets through an equally impressive hydraulic network. Excavations have exposed stone-lined drainage channels, underground sewers, and carefully graded water management systems extending across large portions of the city. Laser surveys demonstrate that many channels maintain extremely gentle gradients while still allowing continuous drainage and minimizing sediment accumulation. Such precision would have required accurate surveying across considerable distances. Roman instruments, including the chorobates and groma, are known from historical sources, yet no surviving document explains exactly how surveyors achieved such consistent elevation control throughout an expanding urban landscape. The infrastructure continues to function as evidence of remarkable practical engineering, while revealing almost nothing about the field techniques used to establish it. The famous hypercaust heating systems illustrate the same pattern. Villas and public bathhouses circulated hot air beneath suspended floors, supported by hundreds of small brick pillars, before directing heat upward through hollow wall flues. Modern computational fluid dynamics simulations demonstrate that relatively small changes in pillar spacing, chamber height, or flue dimensions can significantly alter heat distribution. Excavated hypercaust systems at Augusta Raurica nevertheless indicate surprisingly uniform thermal performance across large interior spaces. Roman builders evidently understood airflow and heat transfer well enough to design efficient systems, but whether that understanding came from mathematical reasoning, standardized construction rules, or generations of accumulated practical experience remains impossible to determine from the archaeological evidence alone. Even the city's urban layout raises questions that remain only partially answered. Streets follow an organized grid, extending across much of the settlement despite irregular topography. High-resolution surveys reveal remarkably small cumulative alignment errors, considering the available surveying technology of the 1st century BCE. Roman land surveyors clearly possessed sophisticated geometric methods, yet historians still debate how such accuracy was maintained while expanding an entire colonial city across uneven terrain without modern optical instruments. The theatre offers another example where the finished achievement survives while its design logic remains uncertain. Seating approximately 10,000 spectators, it remains among the largest Roman theatres north of the Alps. Acoustic studies indicate that speech projected from the stage can still travel efficiently through the seating area despite centuries of structural loss. The geometry reflects a sophisticated understanding of sound propagation, but no surviving architectural treatise explains how builders optimized proportions for each individual location. Whether these results emerged from mathematical calculation, accumulated empirical knowledge, or repeated full-scale experimentation remains unresolved. One discovery revealed that Augusta Raurica was also deeply connected to the wider economic world. In 1961, archaeologists uncovered one of the largest Roman silver treasures ever discovered in Switzerland, containing more than 270 silver objects with a combined weight approaching 58 kilograms. Scientific analysis indicates that the collection consists of silver originating from multiple production regions within the empire rather than a single local source. The treasure demonstrates enormous wealth and long-distance exchange, yet its careful concealment remains unexplained because its owner never returned to recover it. The silver preserves evidence of imperial commerce, while simultaneously reminding archaeologists how much of the human story has disappeared. Lucus Feronii was not uncovered beneath a vanished forest in a single dramatic excavation. The site lies near modern Capena in Lazio, approximately 28 kilometers north of Rome, where the Tiber Valley opens beneath Mount Sorate. Archaeologists began systematic investigations in 1952, and the ancient settlement was securely identified the following year. What emerged was not simply a Roman town, but a place that had changed from a sacred grove into a commercial sanctuary and finally into an organized colonial center. Long before monumental streets and public buildings appeared, Lucus Feronii was associated with Feronia, an Italic goddess connected with fertility, agriculture, and liberation from slavery. Its position was unusually important because it stood near the boundaries of several cultural regions. Sabines, Felici, Etruscans, Latins, and Capenates could meet there without entering the political center of another community. Religious festivals therefore became major markets, drawing farmers, craftsmen, and merchants toward the sanctuary. Livy records that the temple accumulated so much gold, silver, and bronze that Hannibal deliberately plundered it in 211 BC, showing that this apparently rural grove had already developed a complex economic infrastructure centuries before the Roman colony existed. The central engineering question begins with that transformation. A sacred landscape was not empty land available for unrestricted construction. Its trees, altars, boundaries, and ritual paths carried legal and religious meaning. Yet during the late Republic and early imperial period, the area acquired a paved forum, a basilica, temples, shops, baths, roads, and eventually an amphitheatre. The colony, known from inscriptions and ancient geographical sources as Colonia Julia Felix Lucoforensis, was probably organized under Augustus for veterans, Roman planners therefore had to impose civic order without completely erasing the sanctuary that gave the settlement its identity. The excavated forum reveals how carefully the new town was fitted against the older sacred zone. Its stone paving survives in sections, while a portico extended along the western side. On the eastern side, beside the ancient sanctuary, archaeologists found a long basin associated with an aqueduct. At the northern end stood the civic altar of Feronia, the basilica, and, behind it, a richly decorated augusteum containing marble and an opus sectile. Pavement. Rather than placing the religious complex at a distance, the builders integrated it directly into the administrative center. This arrangement suggests a planned compromise between old ritual boundaries and new colonial architecture, but no surviving survey plan explains how the transition was calculated or which earlier structures were removed, buried, or preserved. That uncertainty became more significant when geophysical research revealed that the visible ruins represent only a fraction of Lucus Feronii. Across 3 field seasons, researchers used magnetometry and ground-penetrating radar to examine areas inside and beyond the archaeological park. The magnetometer survey covered approximately 12.5 hectares, collecting samples every 0.25 meters along traverses spaced 0.5 meters apart. Targeted radar work used a 400 MHz antenna and examined about 1 hectare in greater detail. These measurements exposed roads, walls, courtyards, possible workshops, cisterns, and agricultural features without physically excavating them. South of the forum, radar surveyed a zone measuring approximately 143 by 60 meters. Beneath the surface, it detected a concentration of interlocking structures arranged around a corridor nearly 80 meters wide. Most archaeological remains lay between 30 centimeters and 1 meter below ground, directly above shallow bedrock, and many of the high-amplitude reflections were consistent with well-preserved brick or stone walls. One square structure may contain a central courtyard surrounded by regular rooms, yet its purpose cannot be confirmed without excavation. The scientific instruments can reconstruct geometry, but they cannot determine whether the building served as a residence, workshop, warehouse, or institution. The newly mapped settlement also challenges the familiar image of the Roman grid. Lucus Feronii did possess major routes, conventionally called the Via Tiberina and Via Capinate, but buildings appear to have developed mainly along these corridors rather than filling a uniform rectangular city. Domestic structures radiated outward from the principal roads, while other areas remained open or were divided into gardens, production yards, and agricultural plots. This creates an unresolved planning problem. The town displays deliberate organization, yet it does not resemble a colonial plan imposed all at once across an empty landscape. Its engineers may instead have extended streets around property lines, ritual zones, and earlier market spaces whose precise forms are now lost. Water management adds another layer to that problem. The excavated basin beside the forum confirms that an aqueduct supplied the civic center, while geophysical anomalies indicate a cistern and a possible wider network of channels extending north and west. Several other possible cisterns were recorded farther north, apparently connected to linear features running outward at near right angles. Researchers have suggested that some of these lines may belong to irrigation, but the channels have not been fully excavated, dated, or hydraulically reconstructed. It is therefore unclear whether they formed one coordinated system or several networks built during different phases of occupation. This matters because Lucus Feronii combined demands that normally required different water systems. A sanctuary needed water for ritual and visitors, a marketplace required cleaning and drainage, baths consumed large volumes, ornamental installations depended on reliable pressure, and agricultural land required controlled distribution beyond the built center. The presence of shallow bedrock may have helped support masonry and retain underground channels, but it also restricted how deeply conduits could be cut. Roman engineers had to coordinate gradients across terrain that gradually slopes toward the Tiber floodplain, yet no complete sequence from source to reservoir, fountain, bath, and outlet has been recovered. Among the strangest discoveries are groups of regularly spaced trenches and circular pits immediately north of the temple and altar. 15 linear anomalies appear at intervals of about 5 meters. The trenches are roughly 90 centimeters wide, while circular cuts measuring around 1 meter in diameter occur between them at intervals of approximately 6 meters. A second group follows another alignment with even closer spacing. Their regularity suggests controlled cultivation, possibly vines supported by planted trees, but their location beside the sanctuary raises a more unusual possibility. They may preserve the physical design of the sacred grove itself. Nearby excavations have identified irrigation channels and pits interpreted as planting holes for fruit trees, while comparable agricultural trenches elsewhere in central Italy range from approximately 70 centimeters to nearly 1 meter wide. At Lucas Feronii, however, the coexistence of linear trenches and large circular pits could indicate the Roman arbustum technique in which vines climbed living trees. The same evidence can therefore be read as a vineyard, an orchard, or a deliberately maintained sacred woodland. Geophysical instruments reveal the pattern with centimeter-level sampling, but they cannot identify the plants that once occupied the cuts, or prove whether cultivation served profit, ritual, or both. The uncertainty surrounding these pits changes how the entire town must be understood. If they belonged to an ordinary vineyard, then agricultural production reached unusually close to the sanctuary and major road. If they formed a sacred grove, the Romans preserved or recreated Feronia's woodland with measured rows rather than leaving it in a natural state. This would mean that an apparently ancient forest tradition was maintained through planned landscape engineering. The grove may have been as carefully constructed as the forum beside it, but its architecture consisted of soil trenches, tree spacing, and irrigation rather than columns and stone walls. Construction chronology is equally difficult to separate. The forum and public buildings contain Republican and Imperial phases. The amphitheatre belongs broadly to the Trajanic or Hadrianic period, and a bath complex was built or transformed during late antiquity. Magnetometry records all buried materials through their physical properties, not their historical dates, so walls from different centuries may appear together in the same plan. Researchers can see that Lucas Feronii shifted from sanctuary to small town, probably during the 1st century BC, but only excavation can untangle which streets, drains, and buildings belonged to each stage. Located on the volcanic Gergovie Plateau in central France, about 8 kilometers south of modern Clermont-Ferrand, stands one of Europe's most underestimated archaeological mysteries. Long remembered as the place where Vercingetorix defeated Julius Caesar in 52 BCE, the plateau preserves evidence of engineering that still raises difficult questions about Iron Age technology. Gergovie is an Iron Age oppidum identified through archaeological excavations beginning in the 19th century and confirmed by extensive research throughout the 20th and 21st centuries, revealing fortified defenses, domestic quarters, workshops, storage facilities, and occupation layers dating mainly to the late La Tène period. The discoveries transformed Gergovie from a legendary battlefield into one of the best laboratories for studying Celtic engineering. Yet every excavation seems to deepen one particular mystery. Beneath collapsed stone walls, archaeologists repeatedly uncovered hundreds of large iron nails, traces of massive timber beams, and carefully arranged masonry belonging to the defensive system known as Murus Gallicus. Julius Caesar described this structure in Commentari de Bello Gallico, and modern excavations have confirmed that his account was remarkably accurate. The walls combined horizontal oak beams locked together by long forged iron spikes, while stone facings and compacted earth formed the exterior. Unlike ordinary dry stone fortifications, this composite design absorbed impact from battering rams instead of shattering under repeated blows. Experimental archaeology has shown that timber frameworks greatly increase resistance to localized collapse because the wooden skeleton distributes mechanical stress throughout the structure rather than allowing cracks to spread through brittle stone alone. Even more surprising is the quantity of iron required to build such defenses. Archaeologists estimate that large sections of Murus Gallicus consumed many thousands of forged spikes, each individually manufactured by blacksmiths. Some surviving examples exceed 30 centimeters in length, while Caesar himself emphasized that the beams were fastened with iron at regular intervals. Reconstructing walls extending for kilometers suggests that several tens of tons of wrought iron may have been required for a major oppidum, making Gergovie one of the largest known consumers of iron in Iron Age Gaul. That conclusion immediately creates another puzzle, because iron production during the late Latène period remained extraordinarily labor-intensive. Producing only 1 kilogram of bloom iron required significant quantities of charcoal, together with carefully selected iron ore, continuous furnace operation, and repeated cycles of hammering to remove slag. Modern archaeometallurgical studies estimate that bloomery furnaces generally converted only a fraction of the ore into usable metal, meaning enormous amounts of wood had to be transformed into charcoal before a single defensive wall could even begin construction. Yet no industrial complex surrounding Gergovie has been discovered that matches the scale implied by its fortifications. Excavations have identified evidence of metalworking, including slag and smithing debris, but nothing capable of explaining where the immense volume of finished iron originated. Some researchers suggest production was distributed among multiple regional workshops connected through extensive trade networks across central Gaul, while others argue that many smelting sites remain undiscovered beneath later settlements or forests. Neither explanation has been conclusively demonstrated, leaving the logistics behind one of Europe's largest prehistoric engineering projects only partially understood. The mystery becomes even greater when transportation is considered. Gergovie occupies a volcanic basalt plateau rising roughly 150 meters above the surrounding plain and covering nearly 70 hectares. Every timber beam, every stone block, and every iron spike had to reach the summit without wheeled machinery, steel cranes, or powered transport. Archaeologists have never identified permanent construction ramps, loading platforms, or hauling installations that would explain how such quantities of material were moved uphill. Wooden sledges, rollers, ropes, and coordinated labor almost certainly played a role because comparable techniques are documented elsewhere in the ancient world. Yet no direct archaeological evidence demonstrates exactly how construction was organized at Gergovie. As with many prehistoric monuments, the finished engineering survives, while the infrastructure that created it has almost entirely disappeared. The design of Murus Gallicus itself continues to impress engineers because it represents a sophisticated understanding of structural behavior long before formal theories of mechanics existed. Stone supplied compressive strength, timber provided flexibility, while iron prevented the framework from separating under impact. Modern structural analysis shows that composite materials often outperform rigid systems because they combine different mechanical properties within a single structure. Whether Celtic builders developed this concept independently through generations of practical experimentation or inherited specialized knowledge from earlier traditions remains unknown. Archaeology reveals mature engineering, but almost no evidence documenting how the design evolved into such an effective defensive system. Beyond its walls, the plateau also demonstrates remarkable urban planning. Excavations have revealed organized residential districts, storage buildings, workshops, roadways, and defensive gateways, distributed according to the natural contours of the volcanic landscape, rather than random expansion. Instead of forcing the terrain into a geometric pattern, builders adapted the settlement to slopes, drainage routes, and natural defensive positions. Geophysical surveys, together with aerial photography, have helped reconstruct parts of this layout, indicating that planning occurred before large-scale construction rather than developing gradually without coordination. Such organization challenges the long-standing stereotype that pre-Roman Celtic communities lacked sophisticated urban planning. Water management presents another unresolved question. Permanent rivers do not flow across the summit, yet thousands of inhabitants may have occupied the plateau during periods of military concentration. Archaeologists have identified wells, cisterns, and evidence for rainwater collection, but these installations alone do not fully explain how a large defended settlement could sustain its population during prolonged occupation or siege. Some researchers propose that additional underground water sources remain undiscovered beneath volcanic deposits, while others believe storage capacity has simply not survived excavation. Until further evidence emerges, the complete hydraulic system remains uncertain. The volcanic geology also introduced engineering challenges rarely discussed outside specialist research. Basalt is substantially harder than the limestone commonly used elsewhere in Gaul, requiring stronger tools and greater labor to shape foundations and defensive platforms. Even where builders relied primarily on local stone, they still had to level uneven surfaces, stabilize slopes, and construct walls capable of resisting erosion on exposed volcanic terrain. More than 2,000 years of weathering have erased many traces of quarrying, preventing archaeologists from reconstructing the exact sequence of construction techniques employed across the plateau. Historical records add another layer to the mystery. Caesar's account of the Battle of Gergovia is one of the main sources, though he focused more on the fighting than the engineering. Amiternum was rediscovered beneath fields near San Vittorino, about 9 kilometers north of L'Aquila, in central Italy's upper Aterno Valley. Excavation of its Roman theatre began in 1878 under Angelo Leosini, while the amphitheatre, whose walls had remained partly visible for centuries, was fully exposed only at the end of the 1960s. Between 2006 and 2013, archaeologists from the University of Cologne used magnetometry, aerial and satellite imagery, total station measurement, laser scanning, and 25 targeted excavation trenches to reveal that the monuments were only fragments of a far larger city, still buried below the plain. The discoveries transformed Amiternum from a collection of isolated ruins into a difficult engineering question. The settlement began as a Sabine center associated with the nearby hill of San Vittorino, but after Roman expansion into the region, around the beginning of the 3rd century BC, its main functions shifted toward the low ground beside the Aterno River and the Via Cassilia. Building an administrative center here required more than placing monuments beside a road. Roman surveyors had to organize streets, public buildings, water infrastructure, and properties across a valley floor divided by a river, while connecting them with older routes leading into the surrounding Apennines. Geophysical maps now reveal a forum, basilica, baths, temples, commercial buildings, an aqueduct and residential complexes arranged around this network. Yet the original surveying sequence remains unknown, because no construction plans or engineering records have survived. The greatest puzzle is the imbalance between the city's monumental infrastructure and its surprisingly small residential population. Amiternum possessed the public architecture expected of an important Roman center, but geophysical investigation found comparatively little densely occupied housing. The most extraordinary residence was a building of approximately 6,000 square meters between the theatre and forum, containing an atrium, 2 peristyles, and a large garden, making it the largest known late Republican or early imperial house of its type. Around it stood administrative, commercial, and religious structures serving a population that appears to have lived largely in villas, farms, and roadside settlements dispersed across the valley, some within a radius of about 5 kilometers. Amiternum may therefore have operated less like a conventional city and more like an engineered service center for a wide pastoral territory, but researchers still debate how traffic, markets, livestock movement, and public gatherings were coordinated through a town with so little permanent housing. This unusual urban system depended on the Via Cassilia, which crossed Amiternum and linked its principal districts. Secondary streets, the aqueduct, and major public spaces developed around the road, while the Forum and Basilica occupied the administrative sector north of the river. Other monumental buildings extended across the southern side, forcing engineers to integrate separate zones into a single functioning landscape. The surviving evidence shows the completed arrangement but not the method by which Roman surveyors transferred alignments over long distances or preserved them through several centuries of rebuilding. Instruments such as the groma, measuring rods, water levels, and sighting devices could produce accurate layouts, yet practical knowledge depended heavily on trained specialists whose procedures were rarely written down in enough detail to reconstruct an entire project. The theatre provides the clearest surviving example of that lost process. Constructed between approximately 50 and 25 BC, it could accommodate about 3,000 spectators and used the natural slope near San Vittorino to support part of its semicircular seating. Its builders still had to calculate the curvature of the cavea, access routes, sight lines, and the relationship between the audience and stage. Near the end of the 1st century BC, they altered the building by adding an architectural stage backdrop and a mechanism for raising and lowering a curtain. Unlike a modern curtain descending from above, Roman theatre curtains were probably operated from a narrow trench in front of the stage by a coordinated system of posts, ropes, and counterweights. At Amiternum, only the structural setting survives, leaving the exact arrangement of timber, metal fittings, and lifting equipment uncertain. The theatre was not a fixed design completed in a single campaign. Brick columns and another staircase were added near the end of the 1st century AD, while decorative limestone, statues, and water features transformed the surrounding area. A large pool once stood in front of the building, and fragments of sculpture and architectural decoration were later recovered from it. Integrating a pool beside a heavily used performance complex would have required controlled water delivery, drainage, and foundations able to limit settlement, but much of this infrastructure remains buried. The theatre continued hosting performances until the middle of the 4th century AD, meaning that its seating, stage machinery, and circulation routes remained repairable for nearly 400 years. A short distance away, the amphitheatre presented a different structural challenge. Built during the second half of the 1st century AD, it held approximately 5,000 spectators and was formed as an ellipse supported by 3 levels of brick arches and vaults. Instead of relying mainly on a hillside, its seating rose above an artificial load-bearing framework. Repeating arches distributed the weight downward, while vaulted corridors carried spectators through the structure, allowing thousands of people to enter, circulate and leave without crossing the arena. The northern facade required restoration during the first half of the 2nd century, showing that Roman builders monitored structural weakness and repaired major components rather than abandoning the monument. Yet its construction history is becoming more complicated. Excavations in 2025 exposed foundation walls belonging both to the amphitheatre and to the neighbouring building traditionally called the Peristyle House. Archaeologists confirmed that this building existed before the amphitheatre, meaning the entertainment complex was inserted into an already occupied urban area, rather than erected on empty land. Engineers therefore had to adapt new foundations, circulation routes, and external spaces to pre-existing architecture. Until larger areas are excavated, it remains impossible to determine how much of the earlier complex was demolished, incorporated, or deliberately preserved beneath the later monument. The function of the peristyle building is itself unresolved. Its scale and position beside the amphitheatre suggest that it may have been a marketplace, the headquarters of a professional association, or a building connected with gladiators and the organization of spectacles. Recent excavation revealed rooms with black and white mosaics and painted plaster, evidence that it was more elaborate than a simple service yard. If it supported the amphitheatre, it may have contained administrative rooms, storage, training areas, or spaces for commercial activity, but no inscription has yet identified its purpose. The mystery is therefore not only architectural, it concerns the operating system behind Roman mass entertainment, including the management of performers, animals, equipment, food, security, and several thousand spectators. Amiternum also stood in one of Italy's most seismically active regions. Archaeological evidence indicates that a major earthquake in the 4th century AD probably damaged the city and contributed to its decline. This does not prove that Roman builders possessed an unknown earthquake-resistant technology, because several buildings were damaged, altered, or abandoned. What the surviving structures do reveal is a practical tradition of thick masonry, repeated arches, vaults, slope-supported seating, and repairable components that distributed loads effectively without modern reinforcement. Determining whether these choices reflected deliberate seismic experience or simply normal Roman construction remains difficult because the same methods were used across regions with very different geological conditions. After the monuments lost their original purposes, their engineering continued to shape later occupation. Houses and a cemetery dating from the 5th to 9th centuries were built over the theatre, while a stone-bordered road crossed its seating area during the 15th century. Elsewhere, a former elite house was reused during the 5th and 6th centuries for metalworking, with imported amphorae and African fine wares, showing that economic connections survived after monumental urban life had weakened. These transformations demonstrate that Roman buildings were not simply abandoned ruins. Their walls, floors, water routes, and open spaces became frameworks for entirely new activities. Minturnae stood where Roman engineering faced one of its most difficult environments, beside the lower Garigliano River in present-day Lazio, southern Italy, near wetlands, shifting sediments, and the point where the Via Appia crossed toward Campania. Rome established a colony here in 296 BC, only 16 years after construction began on the Appian Way. What later emerged was not a minor roadside settlement, but a port city equipped with forums, temples, baths, markets, sewers, an aqueduct, and a theatre capable of holding more than 4,000 spectators. Its ruins reveal the final form of this complex urban system, yet many of the practical decisions that allowed it to function beside a flood-prone river have never been completely reconstructed. The buried city became the subject of major scientific excavation in 1931, when the Italian government authorized a University of Pennsylvania museum expedition directed in the field by American archaeologist Jotham Johnson, working with Amedeo Maiuri. Between 1931 and 1933, the team investigated the Republican Forum, temples and streets north of the Via Appia, while later Italian campaigns exposed the theatre, baths, market, and imperial forum. These excavations recovered monumental architecture, inscriptions, and more than 100 sculptures, but they also exposed something less visible and perhaps more important: a network of carefully coordinated roads, water channels, drains, and sanitation facilities beneath the ceremonial city. The deepest engineering question begins with the landscape itself. Minturnae was not constructed directly in the softest part of the delta, as it is sometimes described, but on a slightly raised Pleistocene beach ridge surrounded by lower alluvial ground and wetlands. This natural elevation reduced the immediate danger of flooding, yet it did not remove the problems created by a high water table, seasonal river changes, and unstable sediment nearby. Roman planners therefore selected the most defensible strip of terrain available and then imposed an orthogonal city plan across it, with the Via Appia serving as the principal east-west axis. The decision shows that their success began not with a mysterious material, but with precise reading of the landscape. What remains uncertain is how much of that ridge was artificially leveled, how foundations were adapted from one district to another, and how builders assessed long-term ground movement without written geotechnical surveys. The surviving section of the Via Appia makes this problem especially visible. At Minturnae, the road became the Decumanus Maximus and passed directly through the monumental center. Its surface was constructed from large blocks of basaltic lava laid over prepared foundation layers, allowing military traffic, carts, animals, and commercial loads to cross the settlement for centuries. Roman road construction is well understood in general, but Minturnae presents a local question. How was a rigid stone pavement maintained where a raised coastal ridge met softer riverine terrain? The visible blocks preserve the finished surface, while most temporary works used to drain, compact, and stabilize the ground disappeared during construction. Archaeologists can document repairs and resurfacing, but they cannot yet reproduce the complete sequence by which different foundation depths and aggregates were selected along the route. This uncertainty continues beneath the streets, where water management was more intricate than the surviving monuments first suggest. Detailed research published on the sanitation of Minturnae has identified public toilets, urinals, shallow washing gutters, and waste channels positioned around heavily used buildings. A large facility beside the basilica may have provided approximately 21 seats, while a smaller toilet west of the theatre could accommodate no more than 5 people. In one preserved section, a gutter descended 0.24 meters over a distance of only 3 meters, a fall of about 8%, sufficient to move water and waste rapidly through the installation. Such measurements prove that gradients were deliberate, yet the complete hydraulic relationship between individual toilets, street drains, water supplies, and final outlets remains difficult to reconstruct, because later rebuilding covered or destroyed crucial junctions. The mystery is therefore not whether Romans understood gravity, but how they coordinated many separate gradients across a city that developed through several centuries. Surveyors could use instruments such as the chorobates, water levels, and sighting tools, while builders relied on plumb lines and measured rods. Even so, every channel had to remain high enough to discharge, low enough to pass beneath buildings, and steep enough to avoid stagnation without eroding its lining. Minturnae was repeatedly enlarged, meaning that new baths, fountains, latrines, and markets had to connect with infrastructure that may already have been generations old. No surviving plan records how these levels were calculated, and excavation reveals only disconnected sections rather than a complete operating network. The arrival of a major aqueduct made this underground system even more demanding. The watercourse is generally dated to the transition from the late Republic to the early Empire and carried water from the Oruncan Mountains over a route of approximately 11 kilometers. Accounts of the surviving structure describe as many as 150 arches, many built in opus reticulatum, before the conduit entered the city near its western gate. The aqueduct supplied a settlement containing public baths, fountains, workshops, and sanitation facilities, all without mechanical pumping. Its flow depended entirely on the controlled loss of elevation between the source and the city, which required Roman surveyors to identify a route shallow enough to preserve water pressure, but practical enough to cross uneven and sometimes marshy terrain. Modern surveys have suggested that parts of the aqueduct were carried across alluvial ground on specially consolidated embankments, and that larger natural changes in elevation may have been exploited at several points, possibly including installations associated with watermills. These interpretations remain provisional, because long sections have vanished beneath agriculture, roads, and later settlement. The surviving arches explain how the conduit crossed open ground, but not how its builders organized the entire operation. Quarrying stone, producing thousands of facing blocks, manufacturing mortar, establishing construction levels over 11 kilometers, and coordinating work crews across wetlands required a logistical system for which no local manual, payroll, or construction diary survives. The masonry itself raises a more restrained but equally important problem. Minturnae contains opus reticulatum, brickwork, stone paving, and concrete cores built during different phases. Roman concrete was not a single universal recipe. Its properties depended on the source of lime, volcanic aggregate, crushed ceramics, water content, and mixing procedure. Scientific studies of Roman concrete elsewhere have shown that volcanic raw materials could produce low permeability matrices and strong chemical bonding between mortar and aggregate, while some marine mixtures developed mineral structures that improved long-term durability. However, those results cannot simply be transferred to every wall at Minturnae. Without systematic sampling across its aqueduct, drains, baths, and foundations, the exact local recipes and the reasons builders selected one mortar for a wet installation and another for an elevated wall remain incompletely understood. That missing knowledge is especially noticeable in the baths and toilets, where masonry had to tolerate constant moisture rather than occasional rain. Channels required smooth, waterproof linings, floor levels had to direct wastewater toward drains, and clean water could not be allowed to mix indiscriminately with sewage. Yet archaeology also shows that Roman sanitation was not modern sanitation. Flowing water could remove waste from public facilities, but contamination remained possible, and an impressive aqueduct did not automatically create a hygienic city. The technical achievement lay in managing large volumes of water with gravity and masonry, not in eliminating disease according to modern standards. Above this hydraulic network stood the Roman theatre, constructed during the early imperial period under Augustus or Tiberius, and later embellished, probably during Hadrian's reign. Its cavea partly rested against older city walls, turning earlier fortifications into structural support, while vaulted passages distributed spectators through the seating area. Estimates place its capacity at more than 4,000 and possibly around 4,600 people. This was not simply an acoustic shell. It was a load-bearing circulation machine that had to support thousands of moving bodies, separate entrances and exits, accommodate stage buildings, and fit into an urban center already constrained by roads and monuments. Grumentum was identified in the upper Agri Valley of Basilicata, southern Italy, near the modern town of Grumento Nova, where surviving ruins revealed a Roman city established during the 3rd century BC. Systematic excavation gradually exposed an unusually complete urban landscape containing streets, temples, houses, baths, a theatre, an amphitheatre, and the remains of an aqueduct. Yet the deeper archaeologists examine the site, the more difficult it becomes to reconstruct the practical engineering system that allowed this inland city to function for centuries. The greatest puzzle begins with water. Grumentum stood on an elevated terrace rather than directly beside a major river, but its inhabitants maintained public fountains, private buildings, and several bath complexes, requiring a controlled and dependable supply. An aqueduct constructed or substantially renewed during the early imperial period carried water toward the city, although much of its original course has disappeared. Researchers therefore combined 19th century descriptions with portable GPS mapping, electrical resistivity tomography, and ground-penetrating radar to search for buried sections. The investigation detected subsurface anomalies compatible with masonry remains, but it could not recover the entire route or determine exactly how Roman surveyors maintained the necessary gradient across irregular ground. This was not simply a channel leading downhill. Water had to arrive high enough to serve different districts while avoiding excessive pressure, leakage, and sediment accumulation. Roman engineers possessed instruments such as the chorobates, water levels, sighting devices, and weighted plumb lines, but the knowledge required to translate repeated measurements into a functioning regional system was rarely recorded. Even a gradient error of only a few centimeters over several hundred meters could produce stagnant sections or destructive acceleration. At Grumentum, the vanished portions of the aqueduct conceal the points where water may have been slowed, filtered, divided, or stored, leaving researchers with fragments of a hydraulic network rather than its complete operating design. The same missing logic appears inside the city. Archaeological work has revealed canals, drains, sidewalks, and porticos integrated into a street system that remained in use through repeated rebuilding over approximately 8 centuries. Documenting this sequence requires photogrammetric recording of individual walls and architectural features, because later repairs frequently obscured earlier phases. The remarkable feature is not that Grumentum possessed an orthogonal Roman plan, but that drainage, roads, and public buildings continued to function as the settlement changed. New construction had to connect with older elevations without reversing water flow or weakening existing foundations, suggesting a long-lived system of measurements, reference levels, and construction records that has almost completely disappeared. This precision becomes particularly visible in the amphitheatre. Built near the northeastern edge of the city, the structure was aligned with the surrounding street axes and positioned close to an entrance route so that crowds arriving from the valley did not have to cross the urban centre. Instead of forcing a symmetrical building onto the landscape, the engineers used the natural difference in height between two terraces. The western seating was supported against the slope, while the eastern side required an artificial substructure. The arena itself was created by cutting and leveling the hill, reducing the amount of masonry and fill needed for the project. Such adaptation appears economical, but it demanded careful control. The excavated slope had to carry thousands of spectators without sliding toward the arena, while the artificially supported side had to settle at approximately the same rate as the section resting on natural ground. Republican masonry in opus incurtum was later supplemented by more regular opus reticulatum, showing that the monument was not built according to one unchanging plan. It was strengthened and modified across different phases, yet the transition between natural soil, retaining structures, and vaulted passages remained stable enough for substantial sections to survive. Excavation of the amphitheatre began in earnest in 1981 after the Irpinia earthquake of November 1980 increased the danger of collapse, demonstrating that seismic movement remained a real threat long after the Roman builders had disappeared. The amphitheatre also contains an unresolved operational problem. Unlike larger arenas equipped with extensive underground chambers, Grumentum had no subterranean system beneath the performance floor. Animals apparently entered through 6 gated openings connected to the surrounding corridor. This meant that handlers had to move animals, performers, and equipment through a compact network at ground level while protecting spectators and preventing opposing movements from colliding. Archaeologists can identify thresholds and passages, but wooden gates, barriers, lifting devices, and temporary partitions have vanished. The surviving masonry reveals the fixed skeleton of the building, not the mechanical equipment that made performances possible. A comparable difficulty surrounds the theatre. Constructed partly against the terrain, it combined carved or prepared ground with masonry seating and architectural scenery. Its success depended on more than outward symmetry. The curvature of the cavea, the height of the stage buildings, the placement of entrances and the inclination of the seating all influenced visibility, crowd movement, and sound. Roman architects understood these effects through geometric practice and accumulated experience, yet there is no surviving design document from Grumentum showing how the theatre was surveyed. Because upper seating, timber elements, and parts of the stage structure are lost, modern acoustic reconstruction can model several possibilities but cannot prove which arrangement originally controlled reflections and speech intelligibility. The public baths required an even more tightly coordinated system. Grumentum contained Republican and Imperial bathing facilities that changed through time, with later floors including black and white mosaics decorated with marine creatures and geometric patterns. Beneath the visible rooms, heated bathing depended on furnaces, raised floors, wall cavities, pipes, drains and reservoirs working together. The hypocaust had to distribute hot gases without concentrating enough heat to fracture the floor, while fresh and used water had to remain separated. Maintaining this balance required constant control of fuel, airflow, and water volume, but the identity of the specialists responsible for operating the system is unknown. Material selection adds another layer to the mystery. Builders used local stone together with lime mortar, concrete, brick, and patterned masonry, but they did not apply a single universal recipe. Mortar had to be adjusted to different functions. Retaining walls needed resistance to moisture and lateral pressure. Vaults required manageable weight and reliable bonding, while tanks and baths needed surfaces capable of limiting water penetration. Modern analyses of Roman mortars elsewhere demonstrate that performance depended on lime preparation, aggregate mineralogy, particle size, curing conditions, and sometimes reactive volcanic material. At Grumentum, however, published evidence does not support the claim that every wall possessed an extraordinary self-healing formula. The more realistic mystery is how builders evaluated local materials and altered their mixtures without standardized laboratory testing. The road network reveals the same dependence on judgment. Grumentum's principal axes organized the forum, temples, and public buildings, while adapting to the long terrace on which the city developed. Roads were not merely paved surfaces, they concealed drains and service channels, and established the levels from which entrances, colonnades, and floors were measured. A small error at the beginning of construction could spread through an entire district. Surveyors could establish right angles with a groma and check horizontal levels with water, but the practical process by which several teams preserved a shared reference across years of work remains uncertain. Archaeologists recover finished alignments, not the stakes, sighting points, and temporary benchmarks used to produce them.
Libica Królewska is an archaeological site in southeastern Poland, near the modern border with Ukraine. Beneath its quiet farmland lies evidence of communities that developed surprisingly advanced technologies thousands of years before writing reached this part of Europe. The site came to wider archaeological attention through systematic excavations and surveys that revealed settlements associated with Neolithic and early Bronze Age cultures, including funnel beaker and corded ware communities. What researchers uncovered was not a lost city or monumental temple. Instead, they found something that may be even more mysterious: evidence of technological knowledge that should have been difficult for small farming societies to develop, preserve, and transmit over centuries. The first mystery involves the construction of large timber buildings. Archaeologists identified post holes indicating the existence of longhouses stretching more than 30 meters in length. Such structures required hundreds of trees and thousands of hours of labor. Experimental archaeology projects conducted in Central Europe have shown that felling a single mature oak using polished stone axes can require hours of continuous work. Building an entire settlement would therefore have demanded a level of organization that seems surprisingly sophisticated for communities without writing, centralized governments, or metal tools. Researchers still debate how these projects were coordinated. Did village leaders organize labor through social authority? Were construction techniques shared between distant communities? Or did specialized builders travel across regions carrying technical knowledge with them? The archaeological evidence remains incomplete. The second mystery concerns settlement planning. Surveys reveal that many structures appear to follow consistent orientations. This may seem insignificant today, but maintaining directional accuracy across multiple generations requires some method of measurement. Without compasses or formal surveying instruments, the inhabitants may have relied on solar observations, landscape markers, or inherited construction traditions. Similar questions have emerged at sites such as Çatalhöyük in Turkey and Skara Brae in Scotland, where surprisingly organized layouts challenge assumptions about early farming societies. The third mystery is perhaps the most fascinating of all: the underground storage pits and food preservation systems discovered throughout the settlement. At first glance, these pits appear simple. They are merely excavated holes in the ground. Yet, closer examination suggests that they may represent one of the most important technological achievements of prehistoric Europe. For early agricultural communities, food storage was a matter of survival. Harvests occurred only once per year, but people needed food every day. A failed storage system could mean famine, disease, and social collapse during winter. Many of the pits found at Libica Królewska display recurring shapes and dimensions, suggesting that their builders followed established design principles. Archaeologists have long noted that underground storage pits can create remarkably stable environmental conditions. Soil acts as a natural insulator, reducing temperature fluctuations compared with surface structures. Modern studies of underground grain storage have demonstrated that temperatures several feet below ground remain significantly more stable throughout the year. In parts of Europe, subsurface temperatures often fluctuate only a few degrees despite large seasonal changes above ground. Such stability slows spoilage and helps protect stored crops. The mystery is how Neolithic communities discovered these principles. Nobody recorded the experiments. No written manuals survive. Yet the evidence suggests that people understood how depth, shape, soil composition, drainage, and ventilation influenced preservation. Some pits appear deliberately positioned in locations with favorable drainage conditions. Others may have incorporated organic linings or coverings that improved storage performance. Researchers continue to investigate exactly how these systems functioned. The challenge becomes even more intriguing when compared with other ancient civilizations. In ancient Egypt, grain was stored in massive state-controlled granaries. In Mesopotamia, written records documented agricultural inventories. At Libica Królewska, However, similar storage goals were achieved without bureaucracies, writing systems, or monumental architecture. The technology itself was invisible. Unlike pyramids or temples, underground storage systems leave few traces behind, yet they may have been equally important to survival. A village capable of preserving grain through harsh winters could support larger populations, withstand poor harvests, and invest labor into construction, trade, and craft production. Some researchers argue that food storage technologies may have played a role in the rise of social complexity across prehistoric Europe. Communities capable of producing and preserving surplus resources gained advantages over neighboring groups. If this interpretation is correct, the humble storage pits at Lubica Królewska may represent an early form of agricultural engineering that helped transform European society. Even today, archaeologists cannot fully reconstruct the knowledge behind these systems. We can measure the pits, we can analyze pollen and plant remains, we can estimate storage capacity, but we still do not know exactly how generations of farmers refined these designs without written science. The fourth mystery involves long-distance exchange networks. Stone tools recovered at the site reveal that some raw materials originated far from the settlement itself. High-quality flint often traveled hundreds of kilometers across Central Europe. Such movement required routes, partnerships, and communication between distant communities. This creates a logistical puzzle. Transporting valuable stone across large distances without roads, carts, or organized states demanded considerable planning. Similar exchange networks have been documented throughout Neolithic Europe, but many details remain unknown. How did traders navigate? How was trust maintained between communities that may never have met before? What mechanisms protected valuable resources during transport? Archaeologists continue searching for answers. The fifth mystery concerns the remarkable precision of flint craftsmanship. Many recovered blades demonstrate extraordinary skill. Producing long, thin cutting edges from brittle stone requires precise control of force and angle. Modern experimental knappers often spend years mastering techniques that prehistoric artisans performed routinely. The existence of such expertise suggests specialized training, yet there is no evidence of schools, manuals, or written instruction. Knowledge must have been transmitted directly from person to person across generations. How this technical education functioned remains uncertain. The discovery of Angkor Thom lies near modern Siem Reap, Cambodia, at the heart of the ancient Khmer Empire. Although European explorers documented the ruins during the 19th century, the true scale of the city remained unknown for more than a century. Everything changed in the early 21st century when archaeologists began using airborne LiDAR technology. By firing millions of laser pulses through the jungle canopy, researchers revealed an enormous urban landscape hidden beneath the forest. What appeared to be a collection of temples turned out to be part of one of the largest pre-industrial cities ever built. Surveys conducted by the Greater Angkor Project revealed an urban complex covering more than 1,000 square kilometers, transforming Angkor from a famous archaeological site into one of the most important engineering mysteries on Earth. The first mystery is the hydraulic system itself. Angkor Thom was not simply a walled city, but the center of an immense network of reservoirs, canals, embankments, spillways, and artificial waterways designed to control seasonal monsoon floods. The scale of this system is astonishing. The nearby West Barre Reservoir measures approximately 8 kilometers long and more than 2 kilometers wide, containing an estimated 50 million cubic meters of water. To put that into perspective, the reservoir holds enough water to fill roughly 20 Olympic swimming pools. Across the Angkor region, multiple reservoirs and canals work together to store, transport, and redistribute water throughout the year. Modern hydrologists studying the system have discovered evidence of remarkable sophistication, showing that water could be redirected through interconnected channels depending on seasonal conditions. During heavy monsoon rains, excess water could be diverted away from critical infrastructure, while during dry periods, stored water could support agriculture. Yet the greatest question remains unanswered. How did Khmer engineers design and maintain such a vast hydraulic network without modern surveying, equipment, advanced mathematics, or industrial construction technology? Even today, managing water across a 1,000 square kilometre landscape requires complex engineering models, yet the Khmer accomplished it more than 800 years ago. The second mystery involves precision city planning. Angkor Thom was established during the reign of King Jayavarman VII in the late 12th century and forms an enormous square approximately 3 kilometers on each side. Massive walls surround the city, while a moat nearly 100 meters wide encircles the entire perimeter. The gates align closely with the cardinal directions. Such precision might appear ordinary on a modern map, but constructing a nearly perfect geometric city within a tropical environment presented extraordinary challenges. Surveyors today use GPS receivers capable of centimetre-level accuracy, yet medieval Khmer engineers possessed no such tools. Nevertheless, they created a city whose overall alignment rivals that of many famous ancient capitals. Similar achievements are often discussed in relation to places such as the Egyptian pyramids or Roman military camps, and Angkor Thom belongs in the same conversation. Archaeologists still debate the exact techniques used to establish these alignments across such a large area. The third mystery concerns the construction of Bayon Temple, the spiritual centre of Angkor Thom. Bayon contains more than 50 towers decorated with over 200 enormous stone faces. Each face rises several meters high and was carved with extraordinary symmetry. Some scholars believe the faces represent Avalokiteshvara, the Buddhist bodhisattva of compassion, while others suggest they may portray Jayavarman VII himself. The engineering challenge is extraordinary because many of these faces sit dozens of meters above ground level, yet their proportions remain remarkably consistent despite being positioned on complex tower structures. Researchers continue to debate whether the faces were carved before the blocks were lifted into position or after construction was completed. If they were carved on the ground, engineers had to achieve near-perfect placement during assembly. If they were carved in place, workers would have needed elaborate scaffolding systems and highly precise measuring techniques. No written records survive to explain how this process was carried out. The fourth mystery involves transportation. Most of the sandstone used in Angkor Thom originated from quarries in the Kulin Hills, approximately 30 to 40 kilometers away. Millions of stone blocks were transported across rivers, canals, and difficult terrain, with some blocks weighing several tons. Modern estimates suggest that tens of millions of tons of stone were moved throughout the Angkor region over centuries of construction. Comparisons help illustrate the scale of this achievement. The Great Pyramid of Giza contains roughly 2.3 million stone blocks, yet Angkor's total building program extended across a much larger urban landscape and required the continuous movement of construction materials over long distances. Archaeologists have identified ancient canals linking quarry areas to the city, suggesting that water transport played a major role. However, the complete logistics system remains poorly understood. Questions remain regarding how many workers were involved, how long transportation took, and how massive stones were loaded and unloaded without cranes. The available evidence remains incomplete. The fifth mystery is hidden beneath the ground. Angkor Thom was constructed in a region heavily affected by seasonal flooding and unstable soils. Despite these conditions, many structures have survived for more than 8 centuries. Engineers appear to have understood drainage, soil stabilization, and load distribution at a sophisticated level. Modern geotechnical studies reveal carefully prepared foundations beneath major monuments, while water management features often worked together with structural engineering solutions. In some locations, canals and reservoirs may have helped regulate groundwater levels. This raises an important question. Did Khmer engineers possess practical knowledge of soil mechanics centuries before the scientific principles were formally understood? The surviving structures suggest that they may have. The sixth mystery concerns population support. Angkor has often been compared with the largest cities of the medieval world. Some estimates suggest that the Greater Angkor region may have supported between 700,000 and 1 million inhabitants at its peak. If accurate, this would place Angkor among the most populous urban centres on Earth during the 12th and 13th centuries. Supporting such a population required enormous agricultural productivity. Rice cultivation depended on reliable water control, while food distribution required extensive infrastructure. Labour organisation had to coordinate construction, maintenance, transportation, and administration. Yet the Khmer left surprisingly few records explaining how this gigantic urban machine functioned. The physical evidence demonstrates success, but the organisational mechanisms behind that success remain largely invisible. The seventh mystery is the collapse of the system. By the 15th century, Angkor's political importance had declined dramatically. Researchers investigating sediment cores, tree rings, and climate records discovered evidence of severe environmental instability. Southeast Asia experienced prolonged droughts interrupted by episodes of unusually intense rainfall, and these extreme climate events may have placed enormous stress on the hydraulic network. Computer simulations suggest that parts of the water management system became increasingly vulnerable over time. Channels eroded, reservoirs accumulated sediment, and infrastructure required constant maintenance. Some scholars believe Angkor became a victim of its own complexity. As the larger the system grew, the harder it became to manage. Yet, no single explanation fully accounts for the decline. Climate change, political conflict, shifting trade routes, and institutional challenges may all have contributed, and the exact sequence of events remains uncertain. The lost city of Tiwanaku is hidden deep in the Sierra Nevada de Santa Marta in northern Colombia, a mountain range that rises from the Caribbean coast to more than 5,700 meters in less than 50 kilometers. Long before Europeans arrived in South America, the Tairona civilization built a network of settlements across these mountains. At the center was Tiwanaku, better known today as Ciudad Perdida, or the Lost City. What makes the site remarkable is not only its age or isolation. The greatest mystery is how a society without iron tools, wheeled transportation, or large draft animals managed to build a city that could withstand one of the harshest tropical environments on Earth for more than 1,000 years. The modern discovery of the city occurred in the 1970s when local treasure hunters, known as huasaqueros, followed ancient stone stairways into jungle-covered mountains. Their discoveries attracted the attention of Colombian archaeologists, who soon realized that the site represented one of the largest pre-Columbian urban centers ever found in South America. Archaeological investigations revealed more than 250 stone terraces connected by roads, staircases, retaining walls, and drainage systems spread across steep mountain slopes. Radiocarbon dating indicates that the city was established around AD 800, making it several centuries older than Machu Picchu in Peru. The first great mystery concerns the engineering of the mountains themselves. Modern engineers understand how difficult it is to construct stable settlements on steep slopes. Landslides, erosion, and heavy rainfall constantly threaten infrastructure. Yet the Tairona transformed mountainsides into a complex urban landscape through the construction of hundreds of artificial terraces. Some terraces required moving thousands of cubic meters of earth and stone. Unlike the Inca, who often built on relatively stable highland plateaus, the Tairona worked within dense tropical mountains where annual rainfall frequently exceeds 4,000 millimeters. The question is simple: how did they know where to build? Modern geotechnical engineers use soil analysis, slope stability calculations, and hydrological models before beginning construction. The Tairona possessed none of these technologies. Nevertheless, many terraces remain remarkably stable after more than 1,200 years. Archaeologists have found evidence that builders carefully selected locations where natural bedrock provided support while retaining walls distributed pressure across the slope. The precision suggests a sophisticated understanding of mountain geology acquired entirely through observation and experience. Yet the methods used to identify safe construction zones remain unknown. The second mystery involves the city's extraordinary drainage system. Tropical rainfall destroys ancient settlements throughout the world. In regions such as Southeast Asia, abandoned cities often disappear beneath vegetation within centuries. Tairona should have suffered the same fate. Instead, much of its infrastructure survived. Excavations revealed an extensive network of stone-lined channels running beneath terraces, plazas, and pathways. These channels directed rainwater away from critical structures and prevented erosion. Engineers studying the system have noted that many channels still function today. Water continues to flow through routes established more than a millennium ago. The scale of this achievement becomes apparent when compared to other ancient civilizations. The Romans constructed famous aqueducts across Europe. The Maya developed sophisticated reservoirs in Central America. The Inca built mountain drainage systems at Machu Picchu. Yet Tairona accomplished comparable hydrological control in one of the wettest environments inhabited by any major pre-Columbian civilization. What remains unexplained is how the system was designed. There are no surviving plans, measurements, or written instructions. The Tairona left no deciphered writing system. Everything depended upon practical knowledge transmitted across generations. Modern archaeology can map the channels, but it cannot fully reconstruct the intellectual framework behind their design. The third mystery concerns transportation. Every stone used in the city had to be moved through rugged terrain covered by dense forest. The Tairona lacked horses, oxen, and wheeled vehicles. South America possessed no equivalent of the draft animals used in ancient Europe or Asia. Yet thousands of tons of stone were transported and positioned with remarkable accuracy. Some terraces contain retaining walls several meters high. Building such structures required coordinated labor, careful planning, and methods for moving heavy materials uphill. Experimental archaeology suggests that teams using ropes, wooden sleds, and human labor could have accomplished the task. However, calculations indicate that moving even a single large stone block up steep mountain slopes would require significant manpower. So this raises a larger question. If constructing one terrace required such effort, how did the Tairona build hundreds? The city appears to represent generations of continuous engineering investment. Archaeologists estimate that the broader Tairona network may have supported tens of thousands of people. Such projects imply organizational capabilities far beyond what earlier researchers imagined for tropical chiefdoms. The fourth mystery is the city's hidden road network. Surveys have revealed stone-paved pathways connecting settlements throughout the Sierra Nevada. Some routes cross steep ridges, descend into river valleys, and climb mountains again. Together they formed a transportation system linking communities separated by difficult terrain. The engineering challenge is comparable to aspects of the Inca road system, which eventually stretched more than 40 kilometers across western South America. While the Tairona network was smaller, it faced unique environmental obstacles. Tropical vegetation grows rapidly. Heavy rainfall erodes exposed surfaces. Rivers frequently change course. Yet many ancient pathways remained usable centuries after abandonment. Researchers continue to debate how these routes were maintained. Did specialized workers inspect and repair roads? Was labor organized through local communities? Or did political authorities coordinate construction across multiple settlements? The archaeological evidence provides clues, but no definitive answers. The fifth mystery involves urban planning. At first glance, Tairona appears chaotic because it follows the contours of the mountains. However, Detailed surveys reveal underlying patterns. Residential areas, ceremonial spaces, administrative centres, and agricultural zones appear carefully organised. Certain terraces occupy strategic positions overlooking transportation corridors. Others are linked to plazas that may have served social or political functions. The city was not randomly assembled, it was planned. This presents a paradox. Many ancient civilizations relied on writing, bureaucracy, and centralized records to coordinate large construction projects. The Tirona appear to have achieved comparable levels of organization without surviving evidence of such systems. The knowledge required to manage labor, resources, and engineering projects remains largely invisible. The sixth mystery concerns agriculture. Supporting a large mountain population required intensive food production. Archaeologists have identified extensive agricultural terraces throughout the Sierra Nevada region. These systems reduced erosion, conserved water, and expanded cultivable land. What remains unclear is how agricultural productivity was maintained over centuries. Tropical soils often lose nutrients rapidly. Modern farmers frequently depend on fertilizers and scientific soil management. The Tirona achieved long-term sustainability using methods that remain poorly understood. Studies of soil chemistry suggest that indigenous farmers may have employed sophisticated land management strategies involving crop diversity, organic enrichment, and landscape engineering. However, direct evidence is limited. Much of the agricultural system vanished long before modern researchers arrived. The seventh mystery is how the Tirona coordinated hundreds of mountain settlements. Despite the difficult terrain, artifacts from different sites show strikingly similar craftsmanship and design, suggesting strong communication networks that spread technical knowledge. Without written records, archaeologists can only speculate. Some believe ritual specialists carried knowledge between communities, while others point to elite family networks built through marriage and trade. Whatever the method, it helped preserve engineering traditions for centuries. The final mystery is the disappearance of the city itself. Spanish chroniclers recorded encounters with Tirona communities during the 16th century. European diseases, warfare, forced resettlement, and colonial disruption devastated indigenous populations throughout the region. By the time the city was abandoned, much of the knowledge responsible for its construction had already begun to disappear. The tragedy is that the physical structures survived, while the engineering knowledge behind them did not. What do you think was the true secret behind Taranaka's survival for more than 1,000 years? Superior environmental engineering, a lost system of knowledge, or something archaeologists have not yet discovered? Agios Athanasios is a Macedonian tomb complex near Thessaloniki, northern Greece, where paintings more than 300 years old still retain remarkable detail and colour. The site raises a question that archaeologists have not fully answered. How did ancient craftsmen create artworks capable of surviving for over 2 millennia, while preserving visual qualities that rival much younger masterpieces? The tomb was discovered in 1994 during construction work near the modern village of Agios Athanasios, approximately 15 kilometers west of Thessaloniki. Archaeologists soon realized they had uncovered one of the best preserved Macedonian tombs ever found. Dating to the late 4th century BC, shortly after the death of Alexander the Great in 323 BC, the monument belonged to an elite member of the Macedonian aristocracy. What initially appeared to be another burial chamber quickly became one of the most important discoveries for understanding ancient technology, engineering, and artistic knowledge in the Hellenistic world. The greatest mystery of Agios Athanasios is not the tomb itself, but the paintings covering its walls. More than 23 centuries after they were created, many figures remain visible with extraordinary clarity. Warriors, banquet participants, garments, weapons, and decorative motifs can still be distinguished in remarkable detail. This preservation is extraordinary when compared with many ancient paintings elsewhere. Most Greek panel paintings have completely disappeared, and even numerous Roman wall paintings suffered extensive fading, despite being hundreds of years younger. Yet at Agios Athanasios, significant portions of the original artwork remain recognizable. Researchers believe the artists employed sophisticated combinations of mineral, pigments, carefully prepared plaster surfaces, and controlled application techniques. Red pigments were likely derived from iron oxides, while black colors may have originated from carbon-based materials. White pigments probably came from lime compounds. The challenge is that modern scientists can identify many ingredients, but fully reproducing the exact durability of the original system remains difficult. The preparation of the wall itself may be even more important than the pigments. Microscopic studies indicate that multiple layers of plaster were applied before painting began, with each layer possessing specific physical properties designed to create a stable surface. The final result acted almost like a protective technological system, rather than a simple painted wall. The comparison with other ancient sites is striking. The famous wall paintings of Pompeii survived roughly 1,900 years before excavation, while the Agios Athanasios paintings are approximately 4 centuries older. Yet in some sections, their visual preservation remains surprisingly competitive. This suggests that Macedonian artists possessed highly advanced practical knowledge of materials science, even if they lacked modern chemistry. The most fascinating question is simple: how much of their knowledge has been lost? Ancient craftsmen left no technical manuals explaining every step of the process, and their expertise may have been transmitted through workshops and apprenticeships before disappearing forever. The tomb itself demonstrates impressive engineering capabilities. The structure consists of a long entrance passage leading to a burial chamber built with precisely cut stone blocks. After more than 2,300 years, major portions remain intact despite earthquakes, weathering, and human activity. Although the dimensions are not as massive as the pyramids of Egypt, the precision is remarkable. Builders had to excavate the site, transport heavy stone blocks, construct load-bearing walls, and create a stable underground environment capable of protecting valuable paintings and burial goods. One of the greatest engineering puzzles involves environmental control. Moisture is among the most destructive forces affecting ancient paintings, as excess humidity promotes biological growth and damages pigments, while temperature fluctuations create expansion and contraction within materials. Yet the tomb remained sealed for centuries while preserving much of its artwork. Archaeologists suspect that the structure's geometry, wall thickness, and burial depth may have unintentionally created a relatively stable microclimate. Whether this was deliberate engineering or fortunate design remains debated, but either way, the result demonstrates a sophisticated understanding of construction principles. The artistic quality visible at Agios Athanasios raises another question: who painted these images? The figures display accurate proportions, detailed clothing, realistic movement, and carefully planned compositions. Such work required years of training, yet unlike many famous artists of later periods, the creators remain anonymous. Ancient literary sources frequently praise Greek painters such as Zeuxis and Apelles. Apelles, who worked during the age of Alexander the Great, was considered one of the greatest artists of antiquity. Unfortunately, none of his original paintings survive. Sites like Agios Athanasios therefore provide rare glimpses into the artistic traditions that once impressed the ancient world. The tomb suggests the existence of highly organized workshops capable of producing elite commissions. These workshops must have possessed specialized knowledge in pigment production, drawing techniques, surface preparation, and large-scale project management. Yet the details of how they operated remain largely unknown. Among the most valuable images are depictions of Macedonian soldiers. The warriors shown in the paintings carry equipment associated with the armies that transformed warfare under Philip II and Alexander the Great. Long spears, shields, armor, and ceremonial clothing appear throughout the artwork. These images provide rare visual evidence for one of history's most successful military systems. Alexander's empire eventually stretched from Greece to Egypt and as far east as northwestern India, covering millions of square kilometers. However, some artistic details differ from traditional reconstructions based on written sources. Certain equipment configurations remain debated among military historians. Were these differences artistic choices, regional variations, ceremonial uniforms, or evidence that modern reconstructions are incomplete? The paintings continue to fuel scholarly discussion. The owner of the tomb remains uncertain. The scale of the monument indicates tremendous wealth. Construction, decoration, and burial preparation required substantial resources, making such projects far beyond the reach of ordinary citizens. Some researchers propose that the occupant belonged to the highest levels of Macedonian society during the turbulent decades following Alexander's death. Others suggest connections to powerful noble families that governed portions of the kingdom during the successor wars. Without inscriptions clearly identifying the deceased, certainty remains impossible. The tomb preserves evidence of status and influence, but not the name itself. This creates one of archaeology's most frustrating mysteries, understanding the achievements of an individual whose identity has vanished. Agios Athanasios required remarkable coordination. Stone, plaster, and pigments had to be sourced and prepared, while artists, engineers, and laborers worked together under a unified plan. Without modern technology or machinery, the Macedonians still completed highly complex projects. The tomb suggests they possessed advanced organizational systems capable of managing resources, labor, and expertise on a large scale, even though the details remain unknown. How did Macedonian craftsmen develop artistic and material technologies so effective that their work continues to survive more than 2,300 years later, while much of the knowledge that created it has completely disappeared? Hala Sultan Tekke, on the southern coast of Cyprus near modern Larnaca, was one of the wealthiest cities in the ancient Mediterranean. More than 200 years ago, ships arrived here from Egypt, Greece, Anatolia, the Levant, and possibly lands far beyond. Yet many of the technologies that made this vast trading network possible remain unexplained. The site was first identified through archaeological investigations during the 20th century, but major discoveries accelerated after extensive excavations led by researchers from the University of Gothenburg, beginning in the 1970s and continuing into the 21st century. What emerged from the ground was not a small coastal settlement, but a major Bronze Age city covering as much as 25 to 50 hectares, making it one of the largest urban centres known in Cyprus during the Late Bronze Age. The discoveries immediately raised a question: how did a city on an island become one of the most important commercial hubs in the entire Eastern Mediterranean around 1500 to 1150 BC? Archaeologists have uncovered evidence of an astonishing international economy. Imported pottery from Mycenae in Greece, ivory from Africa, precious stones originating in Central Asia, Egyptian artifacts, and luxury goods from the Levant have all been found at the site. Chemical analyses indicate that goods travelled thousands of kilometres before reaching Hala Sultan Tekke, and some materials may have crossed distances exceeding 3,000 kilometres. For comparison, the distance between Cyprus and Egypt is roughly 500 kilometres, while the distance between Cyprus and mainland Greece exceeds 800 kilometres. Yet trade connections linked all of these regions into a single economic system. The mystery is not that trade existed, but the scale on which it operated. Without modern navigation equipment, advanced maps, or centralized communications, merchants somehow coordinated an international trading network comparable in complexity to some later Iron Age economies. Researchers still debate how information moved efficiently enough to sustain such extensive commercial activity. Cyprus was the primary source of copper for much of the Eastern Mediterranean during the Bronze Age. In fact, many historians believe the name Cyprus itself became closely associated with copper production. Large oxide-shaped copper ingots recovered from shipwrecks, such as the famous Uluburun shipwreck, demonstrate the enormous scale of Bronze Age metal trade, with some ingots weighing around 25 kilograms each. Thousands of such ingots circulated across Mediterranean trade routes. Producing this volume of copper required mining, transportation, smelting, quality control, and distribution systems operating with remarkable efficiency. Yet archaeologists still struggle to reconstruct the complete industrial infrastructure behind this production. Questions remain about how temperatures exceeding 100 degrees Celsius were maintained consistently in Bronze Age furnaces, how ore quality was standardized, and how production was organized without modern industrial management. The archaeological evidence suggests a sophisticated metallurgical economy, but many of the technical details remain unknown. A city engaged in international commerce should leave behind extensive administrative records. Ancient Egypt produced written archives. The Hittites produced thousands of clay tablets, and Mesopotamian cities generated entire libraries of economic records. Hala Sultan Teki, however, presents a puzzle. The city clearly managed warehouses, imported luxury goods, industrial production, and maritime trade, yet very little evidence survives explaining how these activities were coordinated. Who controlled trade agreements? Who organized shipping schedules? Who tracked incoming and outgoing cargo? The economic system appears highly sophisticated, but much of its administrative structure remains invisible. Excavations reveal carefully organized residential districts, workshops, storage facilities, and industrial zones. This was not random growth. City appears planned. Road systems connected different sectors. Specialized production areas were separated from living spaces, and large storage facilities indicate centralized management of valuable goods. Researchers estimate that several thousand people may have lived here during its peak. Compared with many contemporary settlements across Europe, Hala Sultan Teke exhibited a level of urban organization more comparable to major cities of the Near East. How such planning knowledge developed and spread across the Bronze Age Mediterranean remains uncertain. Every major city depends on water, and this simple fact creates another mystery. Southern Cyprus experiences long dry seasons, meaning that sustaining a large population, industrial production, livestock, and visiting merchants required dependable water supplies. Yet the complete hydraulic system remains poorly understood. Some scholars suggest wells and groundwater sources played a major role, while others believe water collection and storage systems were more sophisticated than currently recognized. The city survived for centuries, indicating that its inhabitants solved a difficult environmental challenge, but exactly how they achieved this remains debated. This may be the greatest mystery of all. Nothing about Hala Sultan Teki makes sense unless its inhabitants mastered the sea. The city's wealth depended on ships, its copper exports depended on ships, its imported luxury goods depended on ships, and ultimately its survival depended on ships. Yet almost none of those ships survive. Wood decays, rope disappear, sails vanish, and the technology that connected entire civilizations has largely been erased by time. Archaeologists can estimate trade routes, but reconstructing the ships themselves is far more difficult. The Uluburun shipwreck, discovered off the coast of Turkey and dating to around 1300 BC, offers one of the few surviving glimpses into Bronze Age maritime technology. The vessel carried more than 10 tons of cargo, including copper ingots, tin ingots, glass, ivory, jewelry, and luxury goods. Its existence demonstrates that late Bronze Age ships could transport enormous loads across open water. But this raises a larger question. How did sailors navigate? The Gamadi compass would not appear for centuries. Accurate nautical charts did not exist, and there were no lighthouses across the Mediterranean guiding vessels from port to port. Yet ships repeatedly crossed hundreds or even thousands of kilometers. Some researchers believe sailors navigated using stars, prevailing winds, seasonal weather patterns, ocean swells, and detailed mental maps passed down through generations. Others argue that Bronze Age mariners possessed levels of practical astronomical knowledge that modern historians still underestimate. Another mystery concerns ship construction itself. Bronze Age shipbuilders created vessels capable of carrying cargo weighing many tons while surviving storms, waves, and long-distance voyages. The engineering challenge was immense. A vessel carrying 10 tons of copper could easily sink if weight distribution was poorly managed. Hull strength, buoyancy, sail design, and cargo arrangement all required sophisticated knowledge. Unlike monumental architecture, which survives for millennia, shipbuilding technology leaves very little evidence behind. As a result, one of humanity's most important technological achievements may also be one of its least understood. Without these ships, Hala Sultan Tekke could never have become a major international port. Yet the methods that made such maritime success possible remain largely hidden beneath the sea. Around 1200 BC, the Bronze Age world experienced one of history's greatest collapses. Major powers declined, trade routes fragmented, cities were destroyed, and entire kingdoms disappeared. Hala Sultan Tekke was caught in this crisis. Evidence suggests the city was eventually abandoned as the wider Eastern Mediterranean trading system unraveled. The causes remain controversial. Earthquakes, drought, warfare, political instability, economic collapse, and the movements of the mysterious sea peoples have all been proposed. No single explanation fully accounts for the evidence. The city that once connected continents simply faded from history. If the shipbuilders of Hala Sultan Tekke could cross the Mediterranean without modern technology, what other ancient engineering secrets have been lost forever? Kleimonas is a prehistoric settlement on the southern coast of Cyprus that may hold one of the greatest unsolved technological mysteries of the Stone Age. How did people more than 10,000 years ago cross the open sea and bring an entire agricultural way of life to an island? The site of Kleimonas lies near modern Agios Tychonis on the island of Cyprus. Radiocarbon dating places the settlement between approximately 9,100 and 8,600 BC, making it one of the oldest farming communities ever discovered on a Mediterranean island. What makes Kleimonas extraordinary is not simply its age. The real mystery is that everything found there suggests the inhabitants did not arrive as primitive explorers. They arrived with crops, animals, construction knowledge, social organization, and a complete farming economy already in place. In many ways, Kleimonas appears less like the beginning of civilization, and more like the successful transplantation of an existing civilization across open water. The site was discovered during rescue excavations conducted by French archaeological teams beginning in 2009. Beneath layers of soil, researchers uncovered circular houses, storage facilities, tools, and most importantly, evidence of domesticated wheat. Radiocarbon analysis soon revealed dates older than nearly all previously known farming settlements on Mediterranean islands. The discovery immediately challenged long-standing theories regarding the spread of agriculture throughout the region. The greatest mystery surrounding Kleimonas concerns transportation. Cyprus has never been connected to the mainland during human history. Even during periods of lower sea levels, the island remained separated from the Levant by roughly 70 to 100 kilometers of open water. To reach it, prehistoric sailors had to navigate beyond the horizon. That alone would have been an extraordinary achievement. However, the inhabitants of Kleimonas appear to have transported much more than people. Archaeologists discovered remains of domesticated einkorn wheat, indicating that settlers deliberately carried cultivated crops from mainland Southwest Asia. Studies suggest that the wheat originated from regions associated with the earliest farming communities of the Fertile Crescent. The seeds had to survive long sea voyages and then be successfully planted in unfamiliar environments. The challenge becomes even greater when considering the logistics involved. A viable farming colony requires food reserves, breeding stock, tools, water containers, construction materials, and enough people to establish a stable population. Modern experimental archaeology has just has demonstrated that transporting even a small number of animals across open sea using primitive vessels is extremely difficult. Yet the settlers of Cleomenas accomplished some far more ambitious. The comparison is astonishing. The famous Viking voyages across the North Atlantic occurred around 1000 AD, roughly 10,000 years after Cleomenas was founded. Viking ships were built using iron tools, advanced woodworking techniques, and centuries of maritime experience. The people who settled Cleomenas possessed none of these advantages. No boats have survived, no harbours have been found, no written records exist, and the technology that enabled these voyages has completely vanished. Some archaeologists estimate that multiple successful crossings would have been necessary to establish a sustainable colony. A single voyage would not have transported enough people or resources. This implies the existence of repeated maritime operations centuries before the invention of sails as commonly understood. The result is one of the oldest and least understood examples of large-scale seafaring in human history. At the centre of Cleomenas stands another puzzle. Archaeologists uncovered a massive circular communal structure, approximately 10 meters in diameter. For a settlement dating to the PPNA period, this is an enormous building. Most houses measured only a few meters across. The central structure was significantly larger than ordinary dwellings and appears to have served a collective purpose. Constructing such a building required far more than simple labor. Workers had to excavate a large circular depression, stabilize its walls, erect supporting wooden frameworks, and create a roof spanning a considerable distance. Without metal tools, pulleys, or mathematical engineering, they managed to construct one of the earliest known public buildings on a Mediterranean island. The structure invites comparison with communal architecture at sites such as Jericho and Göbekli Tepe. Yet Cleomenas stands apart because it appears within an isolated island environment. How did a newly established island community organize enough labor and technical knowledge to construct such a building almost immediately after arrival? The village was not randomly placed. Excavations revealed that many structures were built on carefully prepared terraces cut into sloping terrain. These artificial platforms created stable surfaces for houses and communal facilities. Creating terraces may sound simple, but it involves understanding erosion, drainage, and load distribution. Even today, improperly constructed terraces often collapse after heavy rainfall. The inhabitants of Cleomenas lacked surveying instruments, metal shovels, and written engineering manuals. Nevertheless, they transformed uneven ground into a functional settlement. This achievement resembles landscape modifications seen in much later societies. In some respects, it anticipates techniques that would later become common in Bronze Age agricultural communities thousands of years afterward. How these early settlers acquired such practical engineering knowledge remains uncertain. Another overlooked mystery concerns construction materials. The buildings at Cleomenas were primarily made from earth and timber. Such materials are inherently fragile. Rain, erosion, and biological activity normally destroy them rapidly. Yet archaeologists were able to identify remarkably clear architectural traces after more than 10,000 years. This suggests that builders may have possessed sophisticated methods for selecting soils, controlling moisture, and reinforcing structural walls. Modern studies of ancient earthen architecture show that slight variations in clay composition can dramatically affect durability. Certain mixtures resist weathering far better than others. The people of Cleomenas seem to have understood these properties through experience. Exactly how they prepared their construction materials remains unknown because the organic components have largely disappeared. The evidence from Cleomenas indicates that agriculture did not gradually emerge on Cyprus. Instead, it appears to have arrived already functioning. The settlers cultivated domesticated wheat almost immediately after reaching the island. This raises difficult questions regarding knowledge transfer. Agriculture is not merely planting seeds. Successful farming requires understanding seasonal cycles, soil conditions, storage techniques, crop management, and risk mitigation. A failed harvest on an isolated island could have resulted in catastrophe, yet Cleomenes survived. The community maintained agricultural production long enough to establish a stable settlement. Some researchers describe this as evidence of a highly organized colonization process, rather than spontaneous migration. The settlers may have planned their expansion carefully, carrying generations of accumulated agricultural knowledge across the sea. Perhaps the greatest mystery is social rather than technological. Who coordinated all of this? Someone had to organize voyages, allocate labor, distribute resources, and decide where the village would be built. Yet there is no evidence of kings, governments, writing systems, or formal administration. The settlement demonstrates remarkable coordination without leaving behind obvious signs of centralized authority. This creates a paradox. The achievements visible at Cleomenes suggest a level of planning comparable to much later societies, yet the conventional indicators of political organization are absent. Researchers continue debating whether leadership was temporary, communal, religious, or based on kinship networks. The truth remains unknown.